Yeah, yeah. We can start.
Can we start?
So, good morning. Welcome to this session devoted to INSAR methods. My name is Michele Crosetto. I come from CTTC Barcelona. I co-chair with Ding Ho Tong Min from
Israel.
from
Israel. From Israel.
INRAE. Okay. Where is this?
It's
Toulouse.
No, in Montpellier.
In Montpellier, okay. So we have 4 presentations. Each presentation has a slot of 20 minutes. After the 4 presentations, we have a period devoted to the discussion of the seed questions. This will be right before the lunch break. We can start with the first presentation, which is about estimating peatland surface motion with discontinuous INSAR time series data. It is given by Philip Conroy. Please.
Do we squeeze out Yeah, can we start?
Good morning. Can everyone hear me? Okay.
So go ahead.
Okay, good morning, everyone. My name is Philip. I'm going to talk about trying to estimate the motion of the peatlands in the Netherlands, which is the vast majority of the country, and how we're trying to basically see how the country is slowly subsiding due to the way that water management is done in the country. So if you look in the background here, you can see sort of a typical scene here. This is what a lot of the Netherlands looks like. And you can see there's a sort of very intricate, I should say intimate link between water and land, and how when you make water management decisions, the land sort of reflects what happens afterwards. But what this really is also a talk about is a talk about temporal decorrelation, and how we can actually try to overcome a lot of problems that we have been facing for many years already now when trying to monitor areas like this. So first, I just want to give you a quick overview of sort of what it is we're actually trying to measure, what this signal looks like. So you can see this is a sort of shallow-based deformation time series. And you can see this is basically all motion that's happening in the top few meters of the soil. And you can see throughout the year, we have very strong deformation rates actually around this time of year due to, you know, the rains and stuff. We have a very high dynamic range. Actually, I don't know why I put 8 centimeters here. It's more like 10 centimeters throughout the year that we try to monitor. Okay. Okay, so yeah, once you've taken your seats, I think the talk is also losing a bit of coherence now because we have so many people walking around. So the main problem that I want to address today is basically that we lose coherence every summer. But not only that, we really have a disconnection between our coherent periods as well. And so what we do is we want to sort of differentiate different types of temporal decorrelation, because this has been, you know, talked about for a long time, but we don't really make this distinction between different types of coherence losses. And really what I'm talking about here is if you imagine a sort of epoch, we call it TL here, where you've lost maybe one image, but then in the next image, you know, the coherence comes back and you can make interferograms between the coherent periods. So it's filled in here. That's fine. We're not actually too worried about that. Really what we're more worried about is this other situation here that we call loss of log. And that's when you really lose the connection between parts of the coherence matrix. So we really have not a continuous time series anymore. We have really breaks in the time series that we can't really fill in because there's not enough information here to really do anything with. That can be caused by plowing or harvesting, other agricultural activities. And now I'll show you basically a real version of that, what I just showed you. So you can see basically in red here, I've identified areas where, there's enough to try and make an estimation. And even that is, we're really pushing the limit of how low we can go in the coherence. But you can see that there's very large, parts of this coherence matrix that are just basically noise, especially if you consider the bias in coherence estimation. If you have something that's less than 0.1, there's a very good chance that this is just a bias in the estimator. So there's really nothing connecting these two actual usable periods. So how do we deal with this? The first thing is we just try to identify when can we use the data. So when is there enough data for us to actually do something with? And then we sort of treat these as their own little independent time series to begin with. And we can do some temporal unwrapping. And then we have sort of these little fragments that are unwrapped in time, but they're disconnected still. So we have basically, something here where we think this is sort of what it looks like. We have something here, we think that's what it looks like, but we don't know what's going on in between. And so there's sort of an unknown shift between these things. And right now I've just plotted these with respect to 0. So the first epoch starts at 0 just to show you it's basically unknown. So now we have to sort of find out how to reconnect these. That's where we introduce some additional data to the processing. So basically our idea is we've extracted the maximum that we can from the SAR imagery alone. We need to introduce some additional information to help solve the problem. And first what we do is we start by just collecting land data that we have available for us. So here we have, for instance, a map of all the land parcels in a certain region, and we have a lot of information about these areas actually. So we know the size, we know the shape, we know the water management that's being done there. We know, in theory, the land cover and the soil type as well. So we can combine all this information, and so that we know for each parcel all of this information. And then we can also multi-look along these boundaries so that we can ensure that we have a homogeneous set of data that we're performing our multi-looking under. And then when we do this, we can start finding similarities between neighboring parcels. So if a group of parcels here, like I've highlighted, have the same sort of key parameters that we think determine how the land should move, like land cover, soil type, and the water management decisions that are being made, then it's reasonable to expect them to sort of move the same way as well. So we can group these together, and we can kind of find when are they coherent, when are they not coherent. And so here we have a sort of plot that illustrates that. You can see all of the parcels in the winter periods around January are coherent. And then around April, you begin to lose coherence. But it's a bit of a random process. There's definitely a sort of random element to this. And the idea is actually if you include enough of these parcels that are similar together, you actually have enough data to sort of sample the entire variation throughout the year. So if we just plot them together, we get basically a Swedish spaghetti of time series. So this is a bit of a mess. So now we have all these vertically unaligned segments, but what can we can do something with this. So if we write this sort of a basic equation that sort of describes what we're looking at here, one segment, here, the phases of this segment, they can be described by a certain model that describes the actual movement, and then there's this unknown shift that I introduced as well. So we basically want to find these terms out. And the best way to do that is actually just to look at the change in position in time. So essentially we take the first derivative, and then this shift term just drops out. And that allows us then to just directly estimate basically a model that describes the motion. So in this case, we use a soil model that we developed, but I'm not going to go into that in this talk, but there's a QR code you can scan if you want to look at the preprint for that later. But the idea is basically we have enough information now to estimate a set of model parameters that tells us how we expect the ground to behave based on the discontinuous data that we have. Then once we have that, we can go back into the absolute displacement domain again, right? Now we have these parameters estimated. All we need to do is solve for this shift now, and that's very straightforward. And so now we went from this kind of crazy situation here where we were able to now align all of these, and they fit together quite nicely like a jigsaw puzzle. So this estimated shift can realign the segments. And that gives us essentially a mean displacement time series for that group. So if you look here, this is an example of one of these regions. So you can see we have a mean in blue, and that's the mean of the entire group of parcels that we sort of use to get this model. And then the gray is the dispersion of all the different parcel segments around that. And that gives you an indication of the precision or of how well they fit within this group. Very interestingly, you can also begin to see the effects of climate change on this signal as well. So for instance, in 2018, we had a record hot summer, and you can see there's actually a very dramatic shift down here. And actually, what you see is this is a little bit too short of a time series still, but you have a bit of a permanent loss of soil here, of a few millimeters of soil. And you can imagine as this continues over time, this really adds up. So yeah, that concludes my talk. Basically, the idea is we differentiate different types of temporal decorrelation, and we really try to identify this, what we call loss of lock, that really cuts your time series apart into segments, and that we can bridge this loss of lock by finding similar scatterers that we use to estimate a mean displacement model. Once we have that, we can then get our time series back. And in that time series, we really see the effects of climate stresses on the ground subsidence. And we're also really proud to say that this was the first accurate and validated time series that was done with INSAR of this region. So thanks very much. Check out the preprints below if you're interested, and thanks.
Take your last belief, a little bit decoration at the beginning is well done. Okay, so we have plenty of time for questions.
Hi, yeah, thank you very much. Was the grouping of the parcels automated or a manual process?
It's automated. So basically, we just identify a few parameters in a GIS sort of environment, and you can select based on those parameters.
Thanks.
Hi, thank you for the presentation. And I have another question about the acquisition mode, because I saw that you use descending mode only for these results, but
Sorry, could you speak up a little bit?
sorry, yeah, right. I saw that the results are in descending mode, but did you use or double check with the ascending mode for the same area, just to see?
Yeah, that's a good question. So actually, I didn't get into this. I glossed over some details, but actually what we do is we project the displacements to the vertical, and then we actually have 4 tracks, 2 ascending and 2 descending, that we can then, with this technique, we can actually combine the observations. So
Okay.
we have 4 tracks to generate the full time series.
Okay, thanks.
Yeah.
Okay.
Thank
Take
you.
your last belief.
Thanks.
Thank you again.
Take it away.
we move to the second presentation, which is about spatial unmixing of pixels for more accurate displacement time series obtained with a small baseline strategy, application to France. The talk is given by Aya Shaib.
I am short.
So,
Not yet. Okay, I'll start.
okay.
So, hello everyone. I'm Aya. I'm going to present to you today the work that we've done with Marie-Pierre Douin. We are both from the University of Grenoble-Alpes, and we studied how can we have more accurate displacement time series using the new small baseline subset technique by doing spatial unmixing of pixels. So the background to So the background to this study goes back to a very recent time where the scientific community has noticed the presence of an additional phase bias that is observed mainly on vegetational terrain, like agricultural area or forest. So this bias was not related to any other known effects such as the topographic or atmospheric effect. In the study that I'm showing you here, the study of Ansari et al. 2021, they have shown that the bias is mainly accumulated on short temporal baseline interferograms, where the bias on each simple interferogram is very small. However, its accumulation in time over the whole time series will give us a final velocity map, which is very biased. So they also called this bias as a fading signal because it is mainly accumulating on the short interferograms, and when we get to involve the long-term interferograms, we will be able to reduce the bias, and that's what they show in this figure, where when they use only interferograms of short-term interferograms, we have a bias that is very high, and then when they get to include longer-term interferograms, they reduce the bias until getting to a point where they can mitigate the bias completely. But at this point, they had to use the interferograms of all the possible combination of date. So this is a way to mitigate the bias as long as it's possible to do it. It will be depending on the area that you're working on and the amount of data. So if I want to put in a very simplified sketch what I've just in a very simplified sketch what I was saying. So if we consider an area where we have very few urbanization, a road, a house, and some isolated farms, let's say, and they are all surrounded by croplands and forests. So for this area, if we do a short-term interferogram, we are going to have the croplands relatively coherent, and then we will have a bias that will be accumulating. However, if we take the long temporal baseline interferograms, the cropland will be less coherent or non-coherent, and will obtain noise. And this noise, we are going to, by the multilooking and the filtering of the data, we are going to obtain an unbiased phase around zero. And this is what interests us in this study, because when we do the spatial averaging, we are going to mix the pixels together, and we are going to put some of the bias observed on the agricultural area on the unbiased pixels of the urbanization. So in this study, we are not going to we are not going to see how can we mitigate the bias from when we are using the S-bus technique. However, what interests us is to see how can we do that spatial averaging of the data without having to mix the bias with the useful pixel of the time series. How can we get to have more accurate time series at the end? And for us to do that, we focused on two main steps. First, at the beginning, we started by characterizing the bias that we are working on. So the first step will be to identify these unbiased pixels and try to isolate them. And from there, we are going to try and keep them apart from the bias in order to have more accurate time series at the end. So please. So to do that, we picked a study area which is highly vegetated. It's in France. It is highly vegetated. So our study area is located on the southeastern France, where we had 900 2-lux interferograms that were already processed from Sentinel-1 data of a descending track between August 2016 and April 2021. These data were processed with a new small baseline subset technique. So from those data, we computed the 8-lux, we multi-lux the interferograms, and then we computed the time series using only interferograms at date +1, 2, and 3, which are the interferograms where the bias will be accumulating. So from that, we obtained the time series that I'm showing here to the right, where we can see that it is mainly covered with blue, the blue color, which is the subsidence, the appearance subsidence related to the bias. So if you look at the zoom and we compare it with the simplified length cover of the area, we can see that the blue color is where the blue color or the bias is related to where we have the agricultural areas and the forest. And if we go further and we look rapidly on the temporal coherence in the middle, we can see that these croplands are relatively coherent, as we said before. So from this data, we are going to start our first step of this work and do the characterization of the bias, which we will mainly do it by compare or relate the land cover, the detailed land cover, with different information that we have, such as the velocity and all possible other characteristics of the interferograms. However, I'm not going to show everything here. I'm going just to show the interesting part of the comparison between the land cover and the velocity map. So the first simplest thing to do is to compute the average velocity of each land cover. And by doing that, we can see clearly that in pink, we have the croplands that have mean velocities higher than 1 centimeter per year. And then we have the urban areas that have velocities around 0. And as well, we have the semi-natural areas that have also velocities around 0, such as the natural grassland that is in the mountains or the beaches and dunes. They should not be so biased. And then we have the forest, which have some bias, but it is very low compared to the croplands. So to go further, we did a time series for each land cover. So just to explain what I'm presenting in this time series, for each of the land cover, we take all the pixels of a specific land cover, and we calculate their displacement relative to all pixels of urban areas and at each date, and we obtain these time series. What's interesting when we look at these time series is that I'm showing here 3 examples of the croplands, the soybeans, the intensive grassland, and the vineyard, which resemble to the other also croplands. What's interesting is that we can see that the acquisition of bias is not happening all over the year. However, it's only happening during a specific season, when between March and the end of June of each year. Can you pass me? Wait. So if I try to explain that with our basic knowledge of the agricultural cycle, we know that during the winter there is basically nothing happening on land. So I would assume that it is coherent and it's only 0. However, during the spring, when the plants are growing, we are having this accumulation of displacement over time. And then when it comes to summer, we have the harvesting season. However, we are not seeing any reversible motion, which I can only explain by the fact that when we do harvesting, the pixels become non-coherent, and then we are just going to be noisy, and we will not add or eliminate any displacement. And then the same thing is happening during the autumn. I know that it is much more complex to explain these time series than what I've just said, but it could be an explanation. Please. So the second pixels that are causing bias in the final time series will be the forest. And for those, we can see that we have accumulating bias over time. However, the behavior is interesting, as the bias that is acquired during the spring and the part of the summer is reversible. So I don't really have any proposition or explanation to those. So I'll be open to discussion or propositions later. And by doing that, So by doing the comparison of and the interpretation of the biased pixels and trying to understand their characteristics, I didn't show everything here. But once we've done that, we can go to the next step, which is how to use this information in order to be able to put apart these unbiased pixels in the final time series and obtain more accurate time series. So to do that, we will use this information to weight each pixel that we have, and to weight each pixel that we have. So to achieve that, we used 3 factors. The first factor is the temporal coherence that will give values close to 1 when we are on urban areas. And the second one would be the coherence dispersion. This factor basically shows the consistency of the coherence of each pixel over time. So when we are on urban areas, usually we will have higher values, and when we are on the croplands, we will have low values because they are not coherent all over the year. And the final factor will be the coherence ratio between the summer and the winter. This factor also helped us to isolate the croplands. So we used those 3 factors in the following equation, from which we are going to calculate our weight that we called unmixing coefficient. This weight will have continuous values from 1 to 101. The highest values will correspond to the urban areas, the unbiased pixel that we want to keep at the end. And then the lowest values will correspond to the vegetation, the croplands, and the forest. And in between, we can find the stable non-urban terrains. So if we look at the map to your right, to the right, if we compare the land cover with the unmixing coefficient map that we obtained, we can see that we were able to divide this map into 2 main colors, into red and blue. So we are able to differentiate the agricultural areas from the urban areas. And by doing that, we obtain a time series which is much more accurate. I will go faster. So here I'm showing 2 zooms, 2 examples. And the first time series is the one that was computed without weighting the pixels, and the one to the right is the one computed with weighting the pixel. So if we look at the road in this part, we can see that when we weighted the pixel, we were able to get the information on the road. And then also, if you look here, we can see that we were also able to have information about isolated urbanization that is in the middle of farms, and as well the same is on we can see the same thing on the second example. So if I want to put in a quantitative way what we were seeing on the maps, we computed the mean velocity of each of the unmixing coefficient classes. And so the upper one is for the velocity map that was computed without weighting, and the second one is with weighting. If we compare at first view, we can see that, please, the very first part, which is corresponding to the croplands, and the last part, which is corresponding to the urban areas, they didn't change after what we've done. However, what the big changement was in the middle, where we can see that we obtained this smooth increasing of mean velocity with the decrease in unmixing classes, and this is because we took the urbanized pixels from the middle and we put them at higher unmixing classes, and we did the opposite for the croplands. So to conclude, it is very important. From this study, we've seen that it is important to characterize the pixels when we are walking in a very vegetated area, because from doing that and trying to unmix them by applying a weight to the pixels that we want to keep, we will be able to keep the information at the end and the final time series. From analyzing the bias in France, we have seen that there is up to 2 to 3 centimeters per year of bias that is accumulated on the croplands during a specific season during spring. And then for the forest, there is small bias. However, it is reversible, questionably. So this work was a small part, first part of a larger project that was aiming at mitigating the bias from the products that we used in this study. The afterwork will be presented in a poster. I will be presenting it in the poster this afternoon. So just to give a small overview from these data that we'll be using 3 months and 1 year interferograms only with the 1 to 3 dates that I have shown before, we were able to significantly decrease the bias before and after correction. So we can discuss of this later, and I will stop. I think I did good 20 minutes.
Thank you. So we have time for one question.
I just wanted to ask, should the mean velocity just be 0 if everything was perfect in this scene?
Do you mean in the final
In
velocity?
In other words, any motion that you have in the map is because of this bias. Is that correct?
It is a relative velocity, so it depends from our area. However, yes, if there is no motion, it should be 0.
Should be 0.
Yeah.
Okay, so there, in some cases where you don't have the full covariance matrix, there's no way to actually get rid of the bias.
Yes, we can, in fact. There is other method. Having the full covariance was the method proposed by Ansari AI. I didn't list all the other proposition of how to mitigate the bias. However, even in the study that I will be presenting in the poster afterward, only by using this at 1, 2, 3, 2 months and 1 year, we were able to really significantly improve.
Yeah.
So in other studies, they show that if we need 1, 2, 3, and 4, and then we will get to also mitigate the bias with
Okay, thank you. So, so there is question, but we will keep the last for the last session. With there will be a session C, so we can discuss briefly. Okay.
So we move to the third presentation, which is about a novel algorithm for identification of persistent scatterers. Is given by Mario Costantini from B Open Solutions.
To change. Thank you. Good morning to everybody. So I'm presenting a novel algorithm for point coherent estimation in SAR interferometry. So I don't need to remind to you here in this contest anything about SAR interferometry. Let only me remind that a case step is the identification of coherent points or cluster of points, providing a coherent backscattering over time. So due to this preservation of coherence over time, we can call this point persistent scatterers, regardless of whether the dominant scattering mechanism is point-like or distributed. And so what we propose is a novel algorithm which we will call point coherence estimation, to evaluate in a clean and simple way the interferometric coherence of each single point in an image stack without the need for complex procedures, critical assumption, or approximations. The method, of course, works at full resolution because we don't want biases, as we have seen in the previous presentation, but of course can be applied also to cluster of points with degraded resolutions, like for a multi-look or distributed scattering. But normally we apply it to full resolution because we don't want biases. And based on the coherence and the related noise level estimated by the method we propose, we can select the points, the PS. So the only assumptions we use are the very well-known and accepted assumptions that large phase artifacts, such as atmospheric delays or orbital effects, are almost identical in points within tens or hundreds of meters. The second assumption is that the phase noise, thermal or the correlation noise, is relatively small with respect to a phase cycle. And the third assumption is that the phase noise has a statistically independent realization in different points. And to be sure of this, we can exclude, if needed, adjacent pixel if the images are oversampled. Then, based on these assumptions, we can derive an equation which can be linear, linking the relative temporal coherence between any two independent close points. And we know that this can be easily calculated because large artifacts cancel out in the phase difference. So we can relate this relative coherence between two close points with the temporal coherence of each of the two single points forming the pair. Then, if we consider a set of many of these pairs, we obtain an overdetermined system of linear equation, which can be solved robustly and at the end obtain the coherence of each single considered point. So let me write some formulas in order to maybe clarify maybe a little bit. So With A, we indicate the pairs of points, and with U, the pairs of times. And as well known, we can represent the phase as a model, which in the simplest case is this model here, but we can use more complex model, including nonlinear effects, plus a residual with respect to the model. So this is the double difference, the double difference of the phase in space and time. Then, again, as well known, we have the temporal coherence formula, which determine the parameters of the model by maximizing the temporal coherence. And again, as well known, the residual with respect to the model can be represented as depends only on the thermal and the correlation noises of the two single points, because atmospheric orbital effects cancel out. So, starting again from writing the coherence, the temporal coherence depends on the residual, as we have seen. Now, let's take the limit for an infinite number of acquisitions, but however, the method works also with a finite number of acquisition. As a normal stack with 40 image works very well. And so the temporal coherence is the expectation value of the phasors of the residuals, the noise residuals, which can be written depending on the noises of the 2 points. And if we assume that the noise realizations in the 2 points are independent, we can write this expectation value as the product of 2 expectation values, and we obtain at the end that the temporal coherence between a pair of independent close points is the product of the temporal coherences of the 2 single points. In the case with the finite number of acquisition, we can obtain a more precise formula, but anyway, this is perfectly good even with the regular number of stacks. Like, as I said, 40, 50 images, so it's perfectly good. So this is the formula, which is always valid regardless of the phase noise distribution probability, with only the 3 assumptions we said before. And what is important is that this formula is valid for all points, including also the bad points. So we don't need to pre-select any good points. We can apply it also to the full stack, full grid, even though we can make a pre-selection if we want, but we don't need. And taking the logarithm, we can obtain a linear equation. And we have so many of these equations for any pair of points that we consider. So we have an overdetermined linear system that can be solved using L1 or L2 solvers efficiently and robustly. And so from in this way, we obtain the coherence on each single point, and by simply thresholding this coherence, we can select the good points. Just one curiosity, if we assume that the noise has a Gaussian distribution, this relation become the well-known relation for combination of independent noise realizations. So let's go to some tests on real data sets. The first stack is a stack of Sentinel images, 86 images, in an area which include urban, rural, bare soil, mountains, different type of terrain. Here we made some details in different areas. In green, we show the points detected by simple methods like signal to crater ratio or amplitude dispersion, methods that can be simply implemented, so just for comparison. In blue, we show the additional points selected with our method. In particular, it's interesting to notice that we find more points along in areas with not only in the city, but also in area with weak scattering, like along the railway or along the river. And this is the final mean velocity obtained after processing, after completing the processing steps. So the additional points are not noisy. And to clarify the points, this is a double dimension histogram showing all the processed pixel. So this is the points that we would select with amplitude dispersion. And this is the points selected by our method, the PCE method. So we see that we lose with respect to amplitude dispersion just a few pixels, but we add a huge number of pixels. The thresholds of amplitude dispersion and PCA method was chosen to have approximately the same number of false alarms, false detection. So this is the same comparison with respect to signal to crater ratio. So this is the point selected by signal to crater ratio. And this is by PCE. Again, we lose with respect to signal to crater ratio just few points, but we add a huge number of points. And this is among the points selected by PCE, the points that would have not been selected by amplitude dispersion or signal to clutter ratio. Another example in an area of Sicily, including Etna volcano, so with strong motions, some enlargements of the volcano, and here we also superimposed the well-known fault lines in the volcano. Again, in the image, some other enlargements to show the behavior of the method in different land cover types. So coming to the conclusions, we have presented the method for point coherent estimation in INSAR. What we believe is nice about this method is that it's very simple and clean, without critical assumption or complex articulated processing, is reliable and accurate, and is computationally fast. The technique based on linking with a linear equation the relative temporal coherence between any two independent close points, which can be calculated as well known. We link this temporal coherence with the temporal coherences of each of the single points forming the pairs, using many of these pairs, we obtain an overdetermined system of this equation, which can be solved robustly and efficiently to determine the coherence of each single point and the related noise level of each single point. What happened? This doesn't go. Okay. So at the end, we obtain a very dense set of measurements, a good coverage also in areas characterized by weak distributed scattering. And also we have, we don't need to make any preselection or any kind of things. We simply obtain an estimation of the coherence on each single point. And based on this, we can select the points. As I said, we apply this to full resolution points because we don't want biases, but the method can be applied also to multi-look or clusters of points obtained by distributed scattering processing. Thank you.
Thank you. It's a very good talk. So we have time for questions or comments. Yes.
Thank you for a very nice talk. It's a very elegant way of selecting good points. I have two questions. I try to be short questions and a short answer, probably. This extra that you did with this method, we can interpret it as these are distributed scattered, that they are coherent over the whole time series, because your method is based on the temporal.
I don't hear very well. Can you repeat, please?
The extra point that you can detect with your method that cannot be detected with amplitude dispersion, so you detect it now. These points, can we interpret them as the distributed scatterers, that they are coherent over whole time series?
Well, first of all, they are full resolution points, so in this sense, we don't have the average and bias. Sometimes these points correspond to weak scattering, which can be not point-like, but more distributed. But the real point is not about if they are distributed or not. The real point is about the fact that you can select.
They are coherent. I agree.
Coherent points over time. Points that keep coherence over time.
And you said it's computationally fast. I can imagine in big areas, this system of linear equations is a huge, huge system of equations. Can you address a little that in the whole frame, if you want to do it and include all the pixels in, this system of equations is quite a large system of equations. And
to be honest, I don't remember, but what I remember is that this method is much faster than the method that we were using before, the PSP method. And by the way, I forgot in the presentation the last point. We are going to provide, we patent this method, we are going to provide this method with additional, the full processing chain as a software as a service. Anyway, I don't remember, but I can check and later with my colleagues and I can tell you later the time. But it's absolutely reasonable.
Okay, thank you. So we have questions, yeah?
Discard bad
arcs.
Bad arcs. No, we can use all arcs, all points and all arcs, because the equation is valid also for bad, very noise points. If you want to make the method even faster, you can make a preselection using some basic methods like, for example, amplitude dispersion or signal to clutter ratio or other methods using a very relaxed thresholds. And then you can apply our method to this set of preselected points, but only if you need to be very fast.
Okay, thank you. So, thank you a lot, Mario. So, at the end, no, it's okay.
Oh,
No? Okay. Just wait a moment, yeah.
So we know that if we apply the traditional, for example, amplitude dispersion pre-selection, we end up with some side lobe and sub-main lobe pixels. How does your method perform in terms of side lobe and sub-main lobe pixels, which are
in terms
present?
of side
And
lobes? Well, I didn't check about this. I don't know. I cannot answer precisely. I mean, the method works on determining the temporal coherence. So you can make maybe a pre-processing to eliminate the side lobes if you want to be more precise, but the method is transparent with respect to this.
Okay, thank you. Thank you a lot, Mario.
Thank you.
yes. Thank you. We move to the fourth presentation, which is about near real-time estimation of unbiased ground displacement time series with INSAR big data. The presentation is given by Scott Staniewicz.
Thank you. So I'm Scott. I'm at JPL, and I'm on the algorithm development team for the Opera project. I've been working on the surface displacement product for Opera. And I'm presenting on behalf of Sarah today. She couldn't be here. But I also wanted to give a thanks to all the colleagues working on Opera. As David said yesterday, it's a pretty big team effort. And so today I'm going to talk about the algorithms we're using for surface displacement for Sentinel-1. Specifically, algorithms developed to meet the low latency requirements of Opera, which, as you'll see, are pretty stringent. So the problem that we have is I'm focusing on INSAR time series analysis for the purposes of extracting surface displacement. The input can be n co-registered SLCs, and the output is a time series of surface displacement, which is relative both in space to some reference point in yellow, and also relative in time to the reference time there. The co-registered SLCs can be in either radar coordinates or geo coordinates. For Opera, we're using GSLCs. And we're processing both PS and DS. And for DS processing, you can roughly categorize into two broad groups, where the first is how the original SBAS posed the problem, where you have some predefined set of interferograms that you form, you unwrap them in some way, and then you perform an inversion to get the surface displacement time series. An alternative is the covariance-based approaches, and these were posed by Guarnieri and Tabaldini and then popularized by Squeezar. And so for these, you take your n co-registered SAR images and you form the n by n covariance matrix, which contains all interferometric pairs. So here we're calling the complex vector of measurements D. You are summing the Hermitian product around some window, summing up the neighborhood where we're calling that omega, which is supposed to be statistically homogeneous pixels. And the result is the covariance matrix, or sample covariance matrix here. And then you perform some optimization there, which is the phase linking. And there have been many approaches that people have come up with over the years. We've listed some. The one that we're using so far in Opera, you can read more about it in Sarah's paper, 2013, which combines the ME of Ansari's 2018 paper, as well as EVD, which is the eigenvalue decomposition, where you simply take the largest eigenvalue of the covariance matrix. So why are we doing the covariance-based approach, and the reason is to avoid bias in the surface displacement. So here are the maps we're looking at. These are average velocity maps derived from INSAR. There's 4 years of data that went into these. The region is the Mojave Desert, and we're looking at this area because this was an area that one of our colleagues, Yuji Zhang, found in 2021 that there's a significant bias in the cumulative displacement that you find, and these result from the shorter baseline interferograms. So on the left, we have a network where there's only nearest neighbor interferograms, so just the 12-day SBAS network. And in the middle, we've implemented the sequential covariance estimator from Ansari's 2017 paper, which utilizes the full covariance matrix. And the right shows the difference in the velocity measurements. And these red streaks, Yuji showed that these actually come from distinct jumps in the cumulative phase time series that align with rainfall events around there. And this is a dry lake, so this is an arid region. And the result in the 4-year displacement time series can be biased up to 5 millimeters per year. And so we need to avoid this kind of bias in the long time series that OPERA is going to produce. And to get the unbiased result there, we implemented this algorithm from Ansari 2017, where, to briefly describe it, you take the full covariance matrix, which can be quite large, and you break it into batches, which she calls mini stacks, and you perform phase linking on each mini stack. And then after you do that, you form what's called a compressed SLC, which we'll talk more about later. And you move on to the next after appending the compressed SLCs to the next mini stack. So the idea of the compressed SLCs is that you retain some of the information from the full covariance matrix, but you also pull much less data, and you avoid the fact that if you had hundreds of SLCs, even something like an eigenvalue decomposition at every pixel of a full resolution output product can be just too computationally infeasible. But one problem with this approach for OPERA is that, as described, you would let a new mini stack fill up as acquisitions come in, and then you perform the next phase linking on the mini stack. But waiting for a mini stack can take a couple months, because even if you have only 10 or 15, that's 10 or 15 times 6 or 12 days. Additionally, these isolated dots on the right, those are the compressed SLCs. And in the paper, there's a final re-optimization where you take all the old compressed SLCs and you perform what she calls a datum adjustment, which is another phase linking. And then you kind of adjust for the offsets that are between the mini stacks, so you overwrite. And we can't really do that for 2 reasons. One, we can't pull that much old data every time we want to process new surface displacement. And we also can't overwrite data that's already archived in the DAC. So we've had to come up with new approaches. And to spell out exactly why, David gave the overview of OPERA yesterday. Again, it's 30-meter output product, line of sight displacement in frames. The 72-hour latency is why we couldn't pull hundreds of gigabytes for every single cloud job that we're doing to get new surface displacement. So we need something that can scale better and be more operationally friendly. So what we've come up with so far, we're calling the incremental estimator. It has the following characteristics: that it utilizes the full covariance information, but it has a much shorter latency for new acquisitions that come in, and it's significantly more operationally friendly. And by that I mean we avoid the datum adjustment at the end, that we no longer need to have a re-optimization and overwriting of old time series data. So to walk through what this is doing with a cartoon that I hope doesn't break everything, we have a time series. We'll say we'll start with a mini stack of size M to start. We would perform phase linking. We archive the displacement D1 to DM. So here we're showing that it's relative to the first day. And we also make a compressed SLC here and archive that compressed SLC for future workflows. When the next one comes in, acquisition M+1, we'll pull that existing compressed SLC. We'll perform phase linking again with that concatenated to the latest M real SLCs. And then we'll archive just the final element here, so just the latest displacement of D1 to M+1. And as more acquisitions come in, the key is that we have the same number of real SLCs, which is easy on our data system. And we pull old compressed SLCs, and we archive just the latest displacement. When we reach a new 2M acquisition, now we have a full mini stack, we can archive the latest displacement, and we can also create a new compressed SLC. And as we save that now, we add that to future acquisitions so that we have a growing size of compressed SLCs. I want to spend a little minute talking about the compressed SLCs, because if you haven't played around with this algorithm, they can seem kind of weird. I thought it was kind of weird at first. But I want to demystify what a compressed SLC is. So if we call the real vector of the vector from the real SLCs Z1 to M from the mini stack, and the result from the phase linking, we can call that Z tilde 1 to M. The output of something like an eigenvalue decomposition, it'll have an arbitrary offset in the phase. So we have to pick a reference point, a reference element, and we multiply all of the other elements by some conjugate. So that sets the first element here's phase to 0. So that's the purple x1 tilde. We multiply everything so that first element has 0 phase. The compressed SLC, it's been described in a way that it's a PCA where you project onto the subspace of the largest principal component. In the end, it's a dot product where you dot Z with Z tilde. And that gives you one complex number that we're calling C1. That's the pixel of the compressed SLC. To show what that looks like, we can write out the summation from the dot product, where the key thing here is the purple x1 tilde. That's in every element of the summation, so we can pull that out in front. And then we see that a compressed SLC really is a base phase from the purple, and it has the same base phase as x1. And then it has a weighting term, which is the rest of the sum. And you can think of that as like a residual phase, or an adjustment to the phase. And to illustrate what that looks like, we can't really look at the SLC. It'll look like noise, like every SLC does. But we can look at interferograms. So here's just an example mini stack over Miami. And we performed phase linking on a mini stack. And now I'm just pulling out one real interferogram between days 1 and day 2, and that's on the left. We multi-look it. And then I swap in for day 1 the compressed SLC1, so C1 times x2 conjugate. And we can see they look rather similar because they have C1 has the same base phase as x1. The difference is that the interferogram on the right looks a little bit cleaner. It looks filtered. And that's how Ansari described it, is that the compression operation acts as a filtering for the SLCs and gives higher coherence when you integrate that into the phase linking. So why am I talking about this? It's because keeping this in mind, we can make a slight adjustment to the sequential algorithm. In that algorithm, as you move forward and compress subsequent mini stacks, the element that they were choosing to pick as the reference vector is the first real SLC, so the yellow x2 here. When you do that, that means every next mini stack will have a different base vector, and so that's why when you write it out, they're all disconnected, and you need that final readjustment step at the end, the datum adjustment. If instead we use the C1 here, the compressed SLC, as the reference vector, now the next compressed SLC that we create, it'll have the same base vector as before, so there will be no more offsets in between subsequent mini stacks. And this means we don't need a datum adjustment at the end. And so to show this, we started with simulation work. This is work that Sarah did. She's done a lot of simulation. There's a lot going on in this slide, but the main things I wanted to take away is that she simulated multiple decorrelation scenarios. So there's fast, slow decorrelating, seasonal, strong and weak. And then she compared multiple algorithms, so an SBAS-like algorithm, the sequential with datum adjustment, and then our new incremental algorithm. And the key is that SBAS performs well when it's fast decorrelating, which is by design. It doesn't perform as well for seasonal or for simulations where there's a fading signal added to the short baseline interferograms. The error grows over time. But for our incremental and sequential, they have very similar error characteristics. They both perform quite well under a variety of scenarios. So in addition to the simulation, we also check the real data, of course. So back to the Mojave Desert, we have the sequential on the left that we showed earlier, and that's with the datum adjustment. And in the middle, we used our incremental estimator to process the 4 years of data. So we basically pretended we were getting new data. We took the 150 images and one at a time, added them to the stack and performed the compressions, and we archived them one at a time. And then we took the average velocity that we see here. And so we see extremely similar results in the final velocity. The majority of the frame agrees within 1 millimeter per year. The colors are in actually low coherence areas. They're agricultural areas that will require better masking and finding of the bad pixels. But the fact that they agree without a datum adjustment and with our incremental approach is extremely promising. You might be wondering, well, are both of these just wrong? Because even though they agree. We checked with GPS. So here we took all the GPS of the area. We projected the average GPS velocity under the line of sight, and we colored it the same as the INSAR. So where there's the same color dot as the INSAR, that's good agreement. Without any correction, any smoothing or temporal filtering or anything, we get about 3.5 millimeters per year for the average velocity. But the Opera project is planning on including a tropospheric delay layer that will be very easy for a user to apply a weather model correction if they so desire. So here we tested that with the ERA5 weather model. And by applying this correction, we actually see 1.3 millimeters per year of agreement between INSAR and GPS. So that was very encouraging. So in conclusion, we have a new incremental estimator that is capable of producing new displacement products in near real time and is operational friendly without overwriting past data. The approach that we took where we modified the compression just slightly, we can actually apply that to the sequential estimator. So we've been calling that the modified sequential estimator. And that's good for processing old historical data because you want to do it in batches. You don't need to do every new SLC one at a time. As with all of the things that Opera is doing, it's open on GitHub, so you can actually run these new libraries to get the incremental or sequential modified phase linking results. And if you are interested, please come talk to us at a poster that is later, and we have more details on the algorithm as well as the PS selection and the SHP selection. Thank you.
So it's a very nice talk on the phase linking application. Yeah. So type of questions. So if no, I suggest we move to the, okay. So, okay.
Why do you not have a displacement bias from closure phase? Do you have ideas why?
When you do the sequential?
Yes.
So I have been thinking about that recently. I don't know if you have read the other papers and have seen their explanations and not found it satisfying. By my best estimate, it's that when you have all possible products, you have the same short baseline interferograms that have bias. So if you only include those, your results will be very biased. As you include more and more pairs that still have information in them, that they're not completely decorrelated, you are weighting out the ones with bias by a bunch of good ones that do not have bias, that are longer term interferograms. And this was also in Yuji's paper that she was showing as you increase the stack size, you decrease the bias, but it's still possible in certain scenarios to have a full covariance where there is some small bias remaining.
Okay. So maybe just allow me to comment on that one for the question. So basically with phase linking, the idea is we combine everything to transform it into one reference image, one reference time series. So that's why we don't have the phase bias or closure phase. So it should be 0 with the closure phase. That is the key idea of phase linking. So thank you a lot. So we move to the C questions. Yeah. Okay. Thank you, Scott.
move from one to the other, then we give the freedom to.
Yeah. So we already prepared for 5 questions. So feel free to discuss each one. If you want to refer to, maybe we can start by the first one, maybe more easy. So what is expected right after intelligent? So basically, the deep learning is something that's one in the BSI processing, and especially in the phase unwrapping, or maybe something related to persistent scatterer identification, or something that's one. So maybe we can focus on each one and then we're moving on. And then maybe we can even to go back and discuss everything. So we have freedom in this session. So for example, maybe I can ask question for the Mario Costantini. So what is your perspective to using deep learning for persistent scatter identification?
Sorry,
so what is your perspective to use deep learning or AI to identify the persistent scatter?
Well, this is a difficult question. I don't know. I think in SAR interferometry, we have a very good and simple physical mathematical model. So these leave not much space for artificial intelligence. I mean, artificial intelligence, it's usually very good when you don't understand anything about what's happening, because the model either doesn't exist or is too difficult. And so you build the model by brute force using so many data, either real or simulated, or using pretest tasks. You know, the most successful cases of artificial intelligence is when you can use pretest tasks, or when you can use a simulated model, because you need so many data to really learn the model from the data. In this case, maybe we have models, so we can use it. So the only thing, the only AI maybe one day could be useful to make methods faster, because if you are able to learn, to train a neural network, to teach to the neural network all the model very well, then the method is very fast. I mean, after you have done the training, it's very fast. On the contrary, with classical methods, you have to invert the model each time. But it's difficult with artificial intelligence, to learn all the methods. I mean, from the data when you already have the method, you already have the model. Anyway, this is my opinion.
Okay, thank you. So, so it means that if we are able to explain something from the output of deep learning, it will be the good perspective to do, right? That's what you mean, exactly?
So, I mean, for computational time, artificial intelligence can be, of course, faster after you have done the training. But doing the training will be difficult, and in particular because we have a very good model, so you have to make a training that, I mean, when you don't have a model, with artificial intelligence, you obtain something better that you can do otherwise because you don't have model. Here is more difficult because you have a good model, so you have to make a neural network that learn a model that is at least as good as the physical one. But if you have done this, the computational time will be better. But,
okay.
I hope this will be not the case.
Thank you.
Any other opinion on the same topic?
Yes.
Wait.
I think there are two other things that might be improved is using artificial intelligence. That is, on the one hand, if we have strong gradients, then...
Can you speak a bit louder?
Yeah, sorry. I think there are two other points which might be helped with artificial intelligence in this case. And one thing is that if there are strong gradients, then they are often mitigated by the distributed scatter estimation. So maybe a network can learn to give this back appropriately. And I also would say up to now, dealing with outliers in the temporal series, there is not so much research about this, and maybe also artificial intelligence can learn this.
Okay, thank you. Yes, Andy, yeah. So, yeah.
Yeah, I'd just like to add to that. I think phase unwrapping is a problem we all still have to wrestle with. And actually, we don't have a good model for phase unwrapping. And I think it's an obvious place where AI can contribute, and already does, actually. I mean, there are several algorithms already out there. And there are people currently working on that. So I think that's a promising area.
Okay, thank you. Is there any, because deep learning, yes, okay, go on, please.
Maybe another point where artificial intelligence can be maybe useful is for the post-processing, you know, because everyone wants to pass from point measurements from pixels, sorry, from PS or DS, whatever, but from measurements, the real users want warnings, alarms about the behavior of a building, of a landslides, and so on. So in this case, which is much more complex, maybe artificial intelligence could be useful. Maybe.
Thank you. So in my opinion, as a function of time, we have a lot of data, and with the computer result will be very strong now. So I think this maybe, it's not really at the moment, but I mean, in future, it should be the best way to go with deep learning or something with the AI, because you know, as a function of time, if we can train a certain model and we can share that model, and then it means with the trained model, people can apply it very quite efficiently with respect to the other one. Of course, as long as we can able to understand what exactly the outputs of deep learning, with it's explainable or something like this one, it can be useful. So maybe we move to the second. No, please. Okay. So thank you. So can we move to the next questions about related to atmospheric estimation using antenna data? So what are the recommendations to apply is systematically, for example, using the goggles, or using the material model, or using the GPS, or what is the way to go? What is the best strategy to go? So you see, even for the last presentation, with the troposophic correction, we can improve a lot in terms of accuracy and performance. So atmospheric correction is always the critical topic. And what is the best way to go?
Silence in the room. We can jump to the third, no problem.
Okay, from my experience, I always using goggles, but the other one I never tried to use, but I don't know what exactly the disadvantage of goggles, for example. Is there any comments from, for example, I am always familiar with goggles correction, and is there any disadvantage for using just that one? Okay, so I speak to myself. So the questions, okay. So We're talking about the time series data with the S-bar. We have problem with phase bias. So basically, how can phase bias can be mitigated or corrected efficiently in time series? So maybe we can move to the speaker number 2. So okay, so AR. So yeah, can you comment on that one, please?
So in order to mitigate the bias, as also in the last presentation, Scott was also said the same thing. If we get to have the long-term, long temporal baseline interferograms in while computing the time series, it will be corrected automatically, and you will not have the bias at the end. However, it could be challenging to do that when we are working in highly vegetated terrain, so it will be hard to be able to unwrap everywhere. But other than this method, there was another method proposed. I don't. However, they were saying that as this bias is linear in time, if we get ferrograms at date plus 1, 2, 3, and until n, for example, we will be able to compute this bias and then eliminate it without using the long-term interferogram. So I don't know if anyone else would.
Yes, yeah. First,
concerning this third sentence, I would recommend to slightly change it, because in my vision, it's a little bit confusing. Let's see if we all agree. If we are talking about multi-look interferograms, and we look at triples, where the multi-looked phase in a triple doesn't give any residual phase, then there is no problem. It's everything okay. It's like single look data, okay? Single look interferograms. So the issue is, in my opinion, pixels where there is closing or non-closing, okay? So pixel where there is closing, that is basically what we use, for example, there is no issue, okay? So the issue then is the closing. So I would rephrase the sentence I wrote. How can we better understand the signals relevant to non-closing multi-looking phases? Because that's, in my opinion, the issue. What's going on when it's non-closing? Of course, this is a complicated issue, because where there is no closing, it's areas where in many places of the world, you extend your time span, you get decorrelation, you don't unwrap, and that's all. But that's the real problem, because all the pixels there is closing, there is no issue at all. And also bias. I think it's a signal, an additional signal. So let's talk about signal instead of bias. That's my recommendation. So once again, and then I close, I recommend to change canceling bias and talk about signal and say that we want to better understand the signal relevant to non-closing multi-looking phases. If you agree, of course.
Okay, thank you a lot. So that's a very good recommendation. So basically, that the fake closures is not the bias. There is some physics inside, so we can see it's from some most something to one. So totally agree with that comments. So Andy, the question over there.
Yeah, I was going to say something else. I mean, I agree with Ricardo. Oh, hello? I agree with Ricardo. I mean, it's a signal, right? And, you know, one person's signal is another person's bias, but it's more interesting in the end to understand it than just to correct it. Nevertheless, there are several talks tomorrow where they are talking about, you know, how to address this. So maybe it's a question that's better addressed tomorrow after that session.
Okay, thank you. Yes.
Maybe I don't understand well because, you know, one question is when there is no closing due to, I mean, bigger no close, let's say, but when you work with multi-look, never perfectly closed due to, and so this causes the propagation of noise. So you never have perfect closing when you work with multi-look. And even this is a small deviation from closing, is the accumulation of this small deviation that integrate with time, if I'm not wrong, but maybe I'm wrong.
Mario, I think you are wrong, sorry. Because just a simple example, if you take an urbanized area, that's for sure you like, because you like persistent scatters, you make multi-look interferograms over an urbanized areas. There are these, let's say, small variations that you think are important because accumulate, make a time series over a multi-looked areas on an urban areas, and you don't get any bias or additional signal. So this small component, to be really effective, it's not just the residual noise coming from the multi-looking, but must be a signal behind. Otherwise, this little flickering doesn't count anything. That's our experience. Maybe we are wrong, but if you want, we can make joint experience and see if I am right or you're right.
Okay. Okay, thank you. Okay, please.
I was just going to make one more comment. What Andy said is that there's a session tomorrow morning. At least 4 of the 5 papers in that session are about this issue, and they've thought a lot more about it, you know, than just what we can say in a few minutes. But I like what Ricardo is saying, in that I don't like the term bias because I think it is misleading. There is an additional signal. There are any number of theories that have been, you know, presented already on this. I mean, we can go over what those are. A lot of these, most of them seem to have in common, though, that this additional signal comes from interference of multiple scattering centers, whether they're distributed spatially or at depth. And there's a nonlinearity in the way that those signals interfere with each other, and that's why it tends to predominantly be in one direction because of the nonlinearity. But this will be described, at least to my knowledge, in some of these papers that are going to be presented tomorrow. And so we could debate it. I mean, I'd be happy to do that over lunch. It's a great subject. But we should hear what the researchers who are addressing this are actually doing.
Okay, yeah. Thank you a lot. So we discussed a lot about the physics interpretation for the non-closure phase. So, and then we move to statistics interpretation now with the phase linking. So, okay, so before we move this one, we go back a little. Yeah, go ahead, please.
So I want to add something to what Howard said. When I first heard about this so-called bias, I was puzzled why it is apparently going in one direction. Found this very strange. And I saw, I think, 2 physical processes which cause this bias. One is soil moisture. So my idea is there's some rain, then the scattering goes not so deep into the soil, and with time this fades. So in a systematic way, scatterers come back to what the radar sees. And similarly, if there is some growing vegetation, it is also the weights of the scatterers in the resolution cell are changed in a systematic way. And apparently this is what causes this systematic signals. And I think we should also have a look what happens at the breaking points. So I think it was the second talk this morning. So after the harvest, there should be happen something. But if you use S-bus and maybe you use singular value decomposition to put together the time series, maybe these jumps which maybe are there are somehow cancelled out. So
yeah, okay, thank you. There's a lot of work to do. So just maybe very quick discussion about the question 4 before we move to the last one, which is the most important. So we move to the statistics point of view for the fake closures with the fail linking. So in that one, can I invite the last speaker, get Scott Stanikowitz? So he's there, he's still there? Yeah, can you comment on that one, please?
Sorry, I'm commenting on how AI could be used for phase linking.
No, the number 4, the one you discussed about phase linking and how it's using in your incremental estimator, something one. Yeah.
Sorry, and then what am I commenting on?
Yeah. Can you comment that question?
Just in general. I don't think I have like the challenges of phase linking. I don't see a real benefit to using AI to speed it up. Currently, so I guess I didn't give any benchmarks or anything because it's still in development. The full frame result that I had for the GPU version of the code, I think I got results in about 3 to 4 hours for 150 images. So if you had a couple of GPUs and you had the data locally, like the biggest time draw would be pulling data, moving it around. Like that's why people are moving to cloud computing. But the phase linking itself is not the burden if you don't have gigantic covariance matrices. So that would obviate the need for an AI, a surrogate model to do it faster.
So basically with the phase linking, we have to do something with the full covariance matrix. And then we have to do something like eigenvalue decomposition. So what do you think if we have something even, okay, with the, now we have 500 images, so we have 500 by 500 covariance matrix. And then if we do compression, so we do something like, okay, so maybe 50 by 50 now. But at the front of time, we have a loss with the center one next generation. So maybe 1,000 by 1,000. What is your perspective?
My current perspective is that we're looking into exactly how many old compressed SLCs we need to pick. It does not look like we need to grow the stack indefinitely. In my early experiments where I kept just the nearest 4 or 5 compressed SLCs in addition to a fixed number of real SLCs, the results were also pretty comparable. I think I was overhearing at IGAR's a conversation with that Ferretti was basically saying he doesn't see much of a use in keeping SLCs that are older than, I don't know, a year or 2. They really do not add much value when you have either full decorrelation by that point, or you have plenty of other SLCs which give approximately the same information. So you don't need to have 500 SLCs in your matrix.
Okay, thank you. So we move to the last critical questions is, what are your recommendations to ESA for targeted R&D activities in the short and medium terms, and in preparation for subcommit mission like B-band biomass, L-band, Rose L, harmonies, center one next generation, and so on? So, yes, Francis.
Yes, just one recommendation would be to look further into the precise orbit determination. So nowadays it takes a couple of weeks before the precise orbits are available. That may not be a problem for every application, but since we're going to get a lot more monitoring applications, I think it would be great if we could reduce the time before precise orbits are available. So the recommendation is that ESA looks further into that.
Okay, thank you.
Any other recommendation for ESA?
About point 2, we didn't comment anything, but maybe this could be a point for ESA. Maybe they could add this systematic processing to the data, at least to have, if you want, you can use them or not, but they could provide systematically this correction to the data. Yeah, atmosphere correction with the option of using or not using it.
Yes, yeah.
Just to say that this is the exactly data product that we are currently producing and should be distributed by the end of the year. No? So it's being produced right now. It's just
right now. It's just on time.
Because we are changing the dissemination system to the new data ecosystem, and they didn't put up yet the flow, but the data is there. Maybe just quickly back to your point, Ramon. It's always good, this kind of things. So you want precise orbits faster, but it's also important to understand how much faster, because maybe it's feasible to change the latency from 20 days to 2, but maybe not to 10 minutes. So.
Yes, that's a fair point, but I think it is, from an applications point of view, there is a little bit of time that we need to get the data down and to get them focused, so within 24 hours is now basically the baseline. So I think that would be the goal, right, to try to get also the orbits available within 24 hours, because at that time you want to do stuff with the data. Great, yeah, thanks.
If there are no comments, I think it's time to close. We have the break for the lunch, and the session restarts at 2.
Okay, thank you a lot for very lovely sessions.
So good afternoon. The streaming will start now with the session on the ground motion service. I am Philippe Ali from the European Space Agency. This session is about pan-European terrain motion mapping with different examples, mainly talking about the Copernicus EGMS service. I was developing the Terra Firma project that was a precursor to the Copernicus EGMS, and Michele Crosetto from CTTC in Barcelona was working also as a partner to this precursor project as the lead of the validation of the Terra Firma services, and now we move to the Copernicus EGMS with this new phase. So Michele, maybe come here, and you start with introducing the first presenter.
I do from here. So good afternoon. The first presentation is about a comparison between the German and the European ground motion services. It is given by Markus Even.
Yeah, thank you for the introduction. Dear ladies and gentlemen, I will show you a comparison of the German and the European ground motion services. And this work is part of a study we have done for the surveying authorities of Baden-Württemberg. The German Ground Motion Service, or BBD, is a national service operated by Federal Institute for Geosciences and Natural Resources, and the European Ground Motion Service is part of the Copernicus Land Monitoring Service, and it is generated by a consortium of 4 companies, and so both ground motion services are based on Sentinel-1 data. And for Germany, both are produced by GAF AG using the IWeb processor of DLR. So although both are produced by GAF AG, there are several differences in processing. Maybe for the calibration, BBD could use more GNSS stations than EGMS. The BBD data stacks start earlier, and the criteria for point selection differ also. First, I will explain you my methods of comparison, and then I will show you different test cases with different ground truth data. So I will compare time series from INSA, GNSS, and leveling and of adjacent points. And the characteristics I use are differences of linear displacement rates and also standard deviations at each location between the signals. To calculate them, I smoothed the INSA and GNSS time series with robust quadratic regression. I used only measurement times in the temporal overlap of BBD and EGMS, and also data have to be interpolated, so maybe that's not so important how I did this. But from the point-wise standard deviations, I also calculated an overall standard deviation according to this formula. For Baden-Württemberg, I will determine coverages of linear infrastructure. I compare BBD and EGMS versus GNSS data. The GNSS stations are at these yellow squares, and I also compare BBD and EGMS directly. For the determination of the coverage, I used shapefiles from motorways, federal roads, and train tracks. And to put a number to these coverages, I determined percentages of segments which contained an INSA point in a distance less than 10 meters from the shape segment. And here you see a table with these percentages. In the rows, you see the different types of linear infrastructure, and the different lengths of segments are used for determination of the coverage. And in the columns, you see results for BBD and EGMS, each for the vertical product for ascending orbit 0.15, for descending orbit 0.66, and I also calculated what would be achieved when ascending and descending orbit are combined, and maybe the most important observations are that the coverage in line of sight is much better than for the vertical product. EGMS also shows a distinctly better coverage than BBD. And if we look at the results of EGMS when ascending and descending orbit are combined, we get quite high percentages. On this slide, we see a comparison with the GNSS data. For BBD, I could use 32 stations, for EGMS 36. And in these histograms, you see comparisons for the ascending and descending orbit, for the vertical product, and for the product in east-west direction. And you see that BBD has a quite small bias, below 1 millimeter a year, and also the dispersion is quite small. EGMS has a slightly bigger bias. And you can also recognize the typical error characteristics of GNSS, which has less precision in vertical direction than in horizontal direction. Yeah, so I think I have not so much time, so I skip this. Here you see a study for the former mining area Saarland. I had a very nice set of leveling data from approximately half-annual measurement campaigns, 10 altogether, and I also with 2,400 measurement points. And here you see the locations of the leveling points, and the color gives the linear displacement rates over the considered period. In the lower diagrams, you see the points of BBD or EGMS in gray, and the colored points are those locations where insert points and leveling points are close by, and the color indicates the difference in linear displacement, which is in the range of -3 to 3 millimeter a year. Here you see the same given by histograms. There is a moderate bias between BBD and leveling, while the bias between EGMS and leveling is much smaller. And if you compare BBD and EGMS, so this bias is again visible. If you now look at overall standard deviations then those look quite nice with below 3 millimeter. I think this is a good general agreement. On this slide, now we are in Western North Rhine-Westphalia. Here we have significant subsidence nearby lignite surface mines where groundwater is pumped off, and also we have an area with uplift caused by flooding of a former hard coal mine. And if you look at the scatter plot of displacement rates, you see that there is a nice agreement. For this I used more than 24,000 points. yeah, the bias between BBD and EGMS is moderate compared to the displacement rates. Here there are also leveling data available, but only 2 measurement campaigns, which makes the estimation of linear trends a bit imprecise. And so we get slightly higher biases and dispersions when we compare INSAR with leveling. So, and here we come now to a test case where BBD and EGMS have problems. This is the cavern storage field at EPE. So there are caverns situated in a salt layer. They are used for storage of domestic gas, brine, and oil. And again, I have nice leveling data. The color again indicates the linear displacement rates. And here we have a complex displacement, which is a superposition of a subsidence caused by shrinking of the caverns because the salt flows. And there are also movements in response to pressure changes in the gas-filled caverns. And also there is some seasonal movement because of changing groundwater levels. Yeah, so the leveling data comprise more than 600 points, and yearly campaigns between 2016 and 2021 could be used. And if you now look at this upper left diagram, you see in magenta a result from leveling, in green and red you see time series from INSAR of nearby points, and you see that there is a big discrepancy, and the EGMS time series shows also some indication of an unwrapping error. In the upper right graphic, you see an INSAR time series at the same location that was produced in our working group, and you see that there is a very steep descent at this time where the unwrapping error happens. This unwrapping error does not only happen at some points, but it occurs in the whole area of strongest displacement. If we compare cumulated displacements between the INSAR measurements and leveling, we see that both BBD and EGMS show big discrepancy of about 40 millimeters. So, and yeah, I assume that this is caused that the linear plus sinusoidal model cannot capture this type of displacement. Yeah, so I come now to an intermediate summary regarding the comparisons. I would say that in general, both services show good performance and good agreement, but if there is a strong spatial temporal gradient, as in EPE, problems might occur. We saw that for the SARPOS stations in Baden-Württemberg, that the calibration of BBD is somewhat better than that of EGMS. And regarding the coverage on linear infrastructure, EGMS has a better coverage. And regarding monitoring of, for example, linear infrastructure, line-of-sight products are superior regarding coverage and also positioning. Finally, I want to show you some interesting example from EGMS. You see here 2 screenshots. So here the vertical product cannot be meaningfully used, but in descending orbit, you see here 3 red points. They have similar time series. One example is here. And from the seasonal pattern, I conclude that they are actually situated on the bridge. And if here in autumn 2017, subsidence sets in. And the surveying authorities only discovered that there is some damage in December 2021, and the damage was so heavy that they had to close the bridge immediately. And in May of this year, it was even blasted. And this is a main east-west traffic connection, which makes no trouble that it is missing. So maybe this indicates that there is some potential for large-scale monitoring with data from BBD or EGMS. And so currently in Germany, several states are introducing in-some monitoring based on Sentinel-1 data, and also Baden-Württemberg is in the initial stage of implementing such a monitoring system. And among others, a possible product could be anomaly detection along this linear infrastructure. Of course, higher resolved data are superior regarding coverage and positioning, but nevertheless, I think these data could provide additional information for an aging infrastructure and also on large scale. So, and I also have some, wishes addressed to EGMS. So, at least in Germany, the use of PS plus DS could provide a better coverage. If the surveying authorities want to install some artificial reflectors, it would be nice to have temporary PS and DS. Yesterday we saw the positioning that could be achieved with Opera, and also there will be soon the ETAT product, so maybe EGMS could also achieve a better point positioning. Yeah, thank you for your attention.
Thank you very much. Time for a couple of questions.
For that bridge example at the end, where the line of sight covered the bridge, but the vertical did not, did the time series you show, like if you showed that to the stakeholders of the bridge, would they have looked at it and noticed there's a problem? Or would the seasonal several centimeters of subsidence look normal to them?
I did not show it to stakeholders. I'm not in contact with the stakeholders, and also this is from EGMS, so it was published later than the problem was discovered. And in BBD, those points have been discarded. So.
Just a comment. In the wish list about the European Ground Motion Service, you say would be desirable to use PS and DS, and this is already the case. The Ground Motion Service of Europe, in the processing were considered both PS and DS.
It depends which company produces the results. As far as I know, in Germany, only PS are used.
Okay, this was not the original intention, because in the original intention, the different service providers should have very minor differences between each other. Alessandro?
Depends on the density of measurement points. If the density of measurement points already exceeds the threshold we set, we said it's fine. So you don't need to go for DS. Otherwise, it's a must. So that was the rationale behind it.
Right.
And indeed, in Germany, as a matter of fact, GAF could meet the requirements without going for a DS analysis.
Yes, but from my own experience with DS processing, you could get much better coverage if you would use them on streets or train tracks.
Good. So, thank you very much for the presentation. We move to the second presentation, which is about the European Ground Motion Service validation. The presentation is given by Joan Sala Calero. Sì, tens la presentació allà baix. L'has vista?
Good afternoon. This presentation is pretty much linked with the one before, but at the European scale. I'm representing the consortium for the validation. It's, as we will see the composition later, made by several partners. And I'm going to go through the validation activities, giving a simple overview, because there are 7 posters complementing this presentation to go more into depth of each of the validation activities we have performed for the EA. As you all know, the GMS is an operational service. It's within one of the 6 thematic services in the land monitoring managed by the EA. So, yeah. And as all operational services, it requires to meet certain standards. That's why you have an independent validation attached to the production. No? The production is done by well-known remote sensing companies, and the validation will produce results in November, the first iteration, and it is a consortium more made of geological institutes and geotechnical institutes together with a couple remote sensing companies, and that complements that knowledge and sits on top of the inventories needed to, let's say, proceed with the validation and agreement analysis, as we will see. Yeah, we're talking about validation, but it's a strong word, especially when you're talking about a data set that is 10,000 million time series at the continental scale. So we prefer to use the word verification as a second look to an already good data set. And we're looking for indexes of agreement between different validation techniques with different precisions, different temporal scales, so it has to be taken into account when looking at the results. Apart from that, we're looking at other criteria, meeting the requirements, usability of the datasets from the user perspective, qualitative analysis done by experts, and completeness and consistency. This, since it has been produced by 4 different entities, it's a necessary check. And also, well, work is done independently by a different consortium, as I presented in the previous slide. Now, yeah, I go back to this point. Sometimes measures are fulfilling different precisions and temporal scales, so we have to be very careful with analyzing the results. 7 different validation activities were conceived. I'm going to go a couple of slides on each one of them, and as I said before, you have 7 posters with the people who performed this validation activity, and you can ask the precise questions to them. Yeah. Apart from that, the sampling strategy to validate this vast data set was not only geographically, so you have validation sites across Europe, 15 total, but also representing the 4 different processing entities or algorithms, and also yeah, the thematic areas of application that were envisaged in the documentation prior to this project. As I said before, the official results consolidated will be published in a report in November that will be accessible through the EA site. The first of the validation activities is the point density check. Yeah, we all know that the INSAR behaves differently depending on the land cover, so it's a matter of looking at density requirements for each of the land cover classes, but also consistency across the different providers. Yeah, we are doing this exercise with Urban Atlas quality control vector data, coming also from Copernicus land. and we chose 12 validation sites. Not only that, but you see on the figure on the right that we do the analysis separating the burst, so we don't consider the overlap to have the nominal, let's say, densities. These are the sites we have chosen. Those are big urban areas, and yeah, coming from Urban Atlas, and 3 sites for each of the providers, and let's say a more difficult site or mountainous area, rural or mountainous area for each of the providers. Second validation activity is performed by NGI. We look for agreement against other ground motion services, like the presentation we saw before with the German ground motion service. We also consider that one. But on top of that, we are comparing it to the Norwegian, Danish, in the Netherlands as well. And we have 2 specific data sets produced with different processing chains, of course. One from IDEA, focused on Mount Etna, so in Sicily, and one from DTU Space on coastal subsidence in Denmark. So that allows us to compare it to more, let's say, focused processing. No? This is just an example of the results you will see in the poster concerning VA2 of NGI. This is the test site I mentioned before, so the Etna volcano, and you see a general agreement between the IREA results and the GMS active deformation areas, so we do the comparison with these polygons. The third validation activity is the comparison with inventories of phenomena. So in here we're seeing, for instance, the national inventories of Spain, France, and Czech Republic concerning landslides. And we see how EGMS, via the extraction of active deformation areas and comparison, how well does it correlate with the existing inventories, and how well does it complement the existing inventories, because we found out that it will allow the mapping of a lot of new landslides that were not mapped because it was a human process. No. Fourth validation activity is more based on expert judgment together with other types of inventories concerning geological layers, lithological, hydrogeological, geomorphological, and geotechnical maps, also done by NGI, the Norwegian Geotechnical Institute. And again, we follow this automated ADA approach, active deformation areas, together with expert judgment. So this is more a qualitative analysis of, and we have different sites tackling different thematics. You'll see La Unión, for instance, in Spain. We have Lisbon, a fault system, also very interesting, and mining in Silesia and Czech Republic, and urban and construction works in Oslo, Norway. Here you see another example. Also, I would encourage you to visit a poster devoted to VA4, sorry. This is correlation between the different soil types and subsidence. So I forward this question to Malte, who's in the audience. And for VA5, these validation activities performed by TNO, Dutch Research Institute. Here we are comparing with stations, GNSS stations that were not used in the production, of course, because that would be biased comparison. And we are comparing the time series basically with different methods. And yeah, we are doing that for the 3 product levels, so the basic, calibrated, and the ortho. You see an example of, actually it's in the Canary Islands with mostly seasonal component. VA6, the one before last, this is a comparison with in situ monitoring. This is done by Geosphere Austria, who sits on top of inventories of, in this case, we are seeing automatic total stations, if I'm not mistaken. And we have other data coming from GPS campaigns, leveling, piezometers, and geodetic monitoring. also provided by the Czech Geological Institute and the Spanish Geological Institute. Here, an example, this is a landslide area in Austrian Tyrol, and we see overall and general agreement with the automatic total stations tracking system. Last validation activity, this is performed again by TNO, and in this case we are using corner reflectors that were installed. It was challenging to find them, but were installed years ago, so coinciding with the production of the beginning of the production of the GMS time series, to have the maximum overlap and study the behavioral time series, but also the positioning in XY and height. Yeah, this is also considering this general agreement, and we produce these indexes in a reproducible system that I will talk about later. Other sites, well, the sites we have is a coastal subsidence site in Denmark, provided by GeoPartner, a ground instrumentation company. The Norwegian corner reflectors were provided by NVE. And then in the Netherlands, we have a couple of sites, and in France, this is provided by IGN, the French Geographic Institute. Last but not least, the way we created this validation is based on a reproducible environment, so a system where we upload both the GMS extraction and the validation data, and we produce notebooks that include explanations, so text, plots, and reproducible algorithms. So the objective is that, well, certify the validation process and also give confidence to the users, no? This environment is, it runs in Terraform and Kubernetes, so it can run in any EU cloud infrastructure. For now, it is only accessible by the EA and us, the validation activity leaders. But the results of this will be published probably at the end of the year. And it gives an extra confidence on the results because all the indexes obtained are actually backed up with code and data. And yeah, that's it.
Hello, thank you very much. Any question about this presentation on validation? There is one question from NASA, if I'm right. Please give your name and ask the question.
Hi, I'm David Bakard from JPL. I had a question about, so you said it's reproducible.
Mm-hmm.
We are also doing something similar, of course, for Opera, and I kind of wonder how reproducible will it be? So the results will be open in the public domain. Do you have any intent for also making the validation strategies like the Jupyter notebooks publicly available afterwards?
Yeah, the Jupyter notebooks will be available, and in the cases, and most cases, we have open data for validation. So depending on the license, the open data, the validation data will also be attached. So basically, you will be able to reproduce the same result, and I think that's interesting, and it adds an added value to the validation process.
Thank you.
Is there any other question? Maybe I have one. I would like to know a very basic question. In your assessment of the performance of EGMS, what is the impact of not having Sentinel-1B?
Well, I actually don't know exact answer of this question. Maybe in the comparison with other GMS.
Your annual product with 12-day samples is as good as with 6-day samples?
In the case of comparison with in situ, where we have higher temporal resolution, there I see some limitation, but for the others, like for instance VA2, it's a comparison to another PSI chain with the same inputs. So in that case, there is no issue. No, apart from that.
Okay.
No.
Thank you.
Thank you very much. We move to the third presentation, which is about validation of the ortho products of the European Ground Motion Service with the previous INSAR-based study, the case study in Gavle City, Sweden. This is given by Nureldin Ahmed Adam Gido.
Yes. Hello, everyone.
This one is free. Okay.
Yeah, thank you. Hello, everyone. This presentation also is in line with the previous one, but maybe in a very small scale, just a city that like 25 kilometers square. So this presentation, it will be like a validation of the ortho product for the EGMS with the previous two INSAR studies, which is one is a little bit old, like 3 years ago, and newly generated result in Gävle city in Sweden. Okay. Yeah. So maybe the first slides not necessary, just general information. As we see, the Gävle city is located in the close to the coast, the Baltic coast in east of Sweden, where we have maybe strong effect from the GIA signal, the glacial isostatic adjustment. And yeah, the rest is general information about the product and the technique that they use it in the EGMS. Yeah, this is the two studies. The first one, it was in 2020 by me and Mohammed, my colleague Mohammed Bagir Bandi and Farah Mars. And in this study, actually, we use SARPRO's software that based on PSI technique. And we have used a number of ascending and descending images that cover that period mentioned here. And we have validated this study with a very long actually leveling record that goes to 45 years in the city. And actually we could get very good agreement between the leveling data and the result that we generated using PSI technique. The second study, it was just recently, maybe just months ago. And in this study, we use G-Query's toolbox, like open source toolbox. And in that one, we try to use the same period that we have it in the EGMS now, with ascending and descending. And the toolbox already implement the PSI technique. So back for the first study, this is the ascending and the descending result that we get it using SARPRO's result in LOS direction. And actually, the both studies actually agreed each other yeah, together, and they shows actually similar localization of deformation in certain places, pointly and area-wise, and the subsidence that we get it, the subsidence rate, it goes to 6 millimeter per year in both studies. I mean in the ascending and the descending one. Then using this ascending and descending data, we could obtain the vertical component and the east-west component. And the first part, I mean the vertical component, we overlaid in the geological map of the city. And maybe we can notice that the density of the point, it become a little bit less in the vertical and also in the east-west direction. The scale shows that the subsidence rate that we get it in the vertical, it goes to like 6 millimeter per year, and for the east-west component, it goes to almost 4 millimeter per year. And this is the result that we get it using Euclid's toolbox. Similar things, we use ascending and descending data, like 100-something data for ascending and descending. And also we can see the similar localization of deformation that we get it in the ascending and descending geometry, with maybe minor differences in the scale that due maybe I think maybe the number of images that we use it, and maybe other things. Then for the comparison with the EGMS, we start firstly to compare the SAR-PROS result in ascending the geometry. And here we start downloading the data because we don't have it in the usually. We download the data and plot it using GIS tool. And then we try to compare pointly and area-wise in the area that we have the similar localization deformation. And we think that we get actually good agreement, but we have some maybe issues we could see maybe in the scale, the difference in the scale between the two studies. We have maybe between 50 to 100 point that out of the range in the GMS, I mean in the EGMS product. If we remove this point, probably we will come very close to that study. Then we apply the same things for the descending geometry, and we have seen also the same localization of deformation with the same change in the scale. I mean, with almost similar number of points. We have almost like 100 points out of 75,000, I think. Almost this is the point that we downloaded for this area. Then here, this table shows the point and area comparison in the same track, and we can see the line of sight rate in both studies in the ground motion of Yabla using SAR-PROS and the EGMS. We can see down. And also we can see, we try also to compare the density of the point, and maybe this is due to the difference in the technique that because we are using PSI, and here I think maybe in Yabla they use both PS and DS. And here we can see actually this is a difference in the point by area in ascending and descending. We can see we have like 279 points in some areas, and in the other area we have just 23 points when we use the PSI. Here also we try to show the differences in a graphic way between the point and areas, and we think that they are closely agreed to each other. Then we come to the vertical component. We try to just to cross-check between them also. And the left one, it's the EGMS component, the vertical, the ortho product. And the right one is SAR-PROS result. And here maybe the first glance we can see in the scale, we have the effect of the GIA signal in the areas. Most of the data, it gives positive actually. It's not displacement, but it's like uplift for that area. The similar things here we can see for the east-west component. We can see also maybe the first things also here we can see the result of the resampling of the data that affect the density of the data. Here we can see in the vertical and even in the east-west. Our result shows very sparse point in the vertical and east-west, but in the EMS product we can see that it looks very dense comparing to that one. And yeah, here also we think that we have effect of the GIA signal in the horizontal component. Here we try actually to compare point by point in the vertical and east-west component. We just select some point randomly, and we can see actually the velocity in the using SAR-pros and the velocity in the EGMS point. And we try actually to keep the distance maximum like 30 meters between the point. And we can see maybe here the differences between the two velocities. It gives almost the value of the GIA signal in the city. We already actually estimate the GIA signal in the city, which goes to 7.7 millimeter, according to the NKJ 2016 GIA model. And the same things for the east-west component. The differences also, which is almost goes to zero. It reflects also the horizontal velocities in the GIA model in the same place. Yeah, this is just we try to show the same result in another way, and the green column it shows the signal. This is the GIA signal that we believe, and the other this is the difference between the two components. This graph also it shows the east-west velocities, and it shows also the signal that we think that belong to the GIA velocity here. Then we came to the result that we get it using GCORIS software, and here just we compare some areas, like 5 areas we selected using GCORIS, and the same area we compute or we estimate the rate of change in the LOS direction. And we can see also maybe the differences between them in this graph. Then generally we think that maybe the two software, they are the result of these two software, they agreed to each other, and also they agreed to the somehow way to the EGMS. At the conclusion, you can say that we did cross-validation of EGMS, the basic and ortho product, with 2 sets of results. The previous one using SAR-pros and leveling data, very long record of leveling data, and the new one using GCORIS toolbox. The two in SAR studies generally, to emphasize on this one, generally agreed well with each other and with the EGMS, and shows similar deformation localization and the rate of displacement at almost 1 millimeter per year agreement in the selected sample point and areas. Maybe it's good also to mention that there are differences in the processing criteria, the type of, maybe we have different type of software and the number of image and the effect of the GIA signal. As expected, we're comparing the EGMS also product with our study. There are additional signal because of ongoing GIA horizontal and vertical motion. Yeah, that's all. Thank you.
Any question about the presentation? Michele, you have a question? Microphone.
Thank you. Can you please comment the big difference in density of PS that you have? You mentioned a factor 10 or factor 20 in the density. Were you very conservative in the processing, so selecting only very, very good points?
Yeah, we try actually to do that, but we think maybe the reason that we are using just PS technique, and we think maybe in YABLA the EGMS based on PS-DS technique. Maybe this is the reason of this, because actually between when we use the G-Chorus, the result of G-Chorus and SARPROS is almost similar, resulting density somehow. But the main differences between those two studies and the EGMS.
Hi, John Dales from NGU, also working with EGMS. No, the PS is strictly PS processing for that area. In the EGMS product, it's strictly based on PS. There's no DS in that product. I'm sorry, I just will confirm that the EGMS data for that area is strictly PS points. There are no PS plus DS processing in that area. So that does not explain the difference.
The difference is not related to the DS. Okay.
Maybe I can complement the answer. Norodin said, yeah, I mean, it's a good point that John mentioned. There is no DS, but the coherence value selected for SAR processing, it was higher than EGMS. I think you showed in a table the difference between different coherence. Maybe this comes to more strict processing things. Yeah, thank you.
Then a quick follow-up comment on that again. Even though the SARPROS was less dense, it did look like there were more outliers in there. It looked a bit noisier than the EGMS as well. So it seems strange that if it's due to more stricter processing that you would get a noisier result then. So I'm not entirely sure what's going on there, but the SARPROS result looked a bit strange compared to the EGMS in that sense.
Okay, if no more questions, thank you very much. We move to the fourth presentation, which is the European Ground Motion Service for Cultural Heritage Monitoring, which is given by Federica Ferrigno.
Okay, good afternoon to everybody. Before to go to the core of the presentation, I would like to give you a really brief introduction of our team. We are for the most geologists, and we work at the Geological Survey of Italy that belongs to the Italian Institute of Environmental Protection and Research. And our main activities are related to the geohazards assessment, to GIS analysis, and INSAR analysis and remote sensing. And we are involved in several projects that deal with cultural heritage monitoring. monitoring. And this is the case of this work that was born with the intention of combining two main activities, the exploitation of the great opportunity provided by the European Ground Motion Service with regards to the huge amounts of ground motion data. And of course, one of the main activity of ISPRA in the general framework of the first extraordinary plan for monitoring and conservation of the cultural heritage in Italy that we have with the Ministry of Culture in Italy. This plan is aimed to monitoring, to the conservation and the proactive protection of the cultural heritage against the multiply risk that can be both natural and anthropogenic. In this case of this work, we have selected among a huge list of cultural heritage in Italy, two of them. The first that I will show you as a case study is the Roman Terme of Baia, that belong to the archaeological era of the Phlegraean fields, and the ancient port of Classe in the really close to the Ravenna city. This slide shows the general approach, the methodology that we used to apply when we are facing to cultural heritage. So we first start with the study of the heritage itself, by the meaning of the construction techniques, eventually restoration history, and its evolution over the time. Then we start with the geohazard assessment by analyzing existing thematic map, and when it's needed, producing some of them. And then we go to the core with the SAR interferometry that can be both already processing data or new processing data made by ourselves. And all these part can help with the ground motion monitoring that is provided with field survey and when it's possible with risk mitigation plan. Here you can see an overview of the Roman Terme of Baia, that is a well-preserved archaeological site that is located in an inactive caldera, ancient caldera. So what we have here is the site map. Then we will see more specifically all the hotspots of the sites. Here you can see these big dome that are really well preserved, that were in which were located the hot springs, the natural hot springs in the area. From a geological and geomorphological point of view, the area is characterized by a sequence starting from the bottom to the top of sarge deposit, volcanic breccia, pyroclastic deposit, and sarge deposits. But the most important thing that we have to say about this area is that it is an important and extraordinary volcanic-related subsidence area with unrest cycles characterized by intense ground uplift and lowering, well known as bradysism phenomena. But in the case of the archaeological site, the main issues was represented by the slope stability. Since it's located spread on the slope of the caldera, you can see in the risk map that the area surrounding the archaeological site is characterized by an high to very high landslide risk. Here we can see a map of a landslide inventory and some picture acquired close to the site, where you can see some rockfall and soil creeps. As you know, the area is characterized also by several geohazards, as seismic and volcanic. On the right side, you can see the location of all the seismic monitoring sector and the pyroclastic density currents invasion probability maps. Starting with the insert data, we decide to analyze the ortho level provided by the European Ground Motion Service, spanning the period from 2015 and 2020. And on the right side, you can see at the site scale the result of this product. And we have processing also the Sentinel-1 data, and the first step was the comparison with the GNSS monitoring network. We selected the Kuma station since it was the only one located outside the caldera, and the projection of the real and absolute movement recorded at the Kuma station shows an overall movement of the Phlegraean era, and it seems to be rising towards the ascending geometry and tilting to the descending one. The amount of the rate of displacement is represented by the two arrows. The red one is about 8 millimeters per year, while the blue one in the descending geometry is about 3.4 millimeter per year. At the site scale, we are facing with it difficult to extract the real potential instability phenomena, since all the region is experiences this uplift phenomena. So we needed to proceed with another approach. That's why, to highlight differential ground motion at the site scale, the difference between the displacement velocity of each measured point and the site mean value was calculated extracting only the measured points included in the archaeological site area. In this way, we were able to detect some PS cluster. Here is the case of the age between the Ambulazio Villa and the Sosandra Villa, in which the time series of the measurement point show a slow movement that was validated somehow during the field survey by the detection of several cracks in the wall. This is another example. Here, the two clusters are located on the top of the archaeological site, and in this case, there is a prevalence of the horizontal movement of slope sliding eastward, and in this case means also seawards, because the site is facing in front of the sea. The last step of this case study was the field survey. And here we can see just the main stops that we had during the field survey. And the main critical issues were represented by cracks, by rockfall, and of course by the invasive vegetation that fortunately has been clarified during the last month. So we are now in the second round of this project. So we will process now the Cosmos SkyMed images, and we will need to have a second field trip for sure. By the way, also a 3D survey has been performed that allows us to select different sectors of the archaeological site by the meaning of the orientation of the cracks, and allow us also to detect wall structure blocks and soil creep phenomena. This is the second case study that is represented by the port of Classe near the city of Ravenna. This is an ancient Roman port that was built to defend all the northern and eastern part of the Adriatic Sea. But unfortunately, due actually to the subsidence phenomena that affected this area back then, this area became very soon marshy, and so the port became unusable. What we have now is just a paved road and some warehouse foundation remains. From a geological point of view, we are in the region of Romagna, so in the Po Valley basin, and we can find, from a lithological point of view, a sequence of marine, delta, lagoon, marsh, and alluvial deposit that lying on complex fault structure. And these geological settings is the cause of the natural subsidence that affect this area by the compaction of the deposit rich in clay or sand. But what happened that this kind of subsidence has a rate of displacement very low. It's like few millimeters per year. But what happened that starting from the 50s, in addition to the natural subsidence of the area, we had also a subsidence related to the human activities, related to the intensive extraction of fluid from the subsoils. In this case, the rates of subsidence could be higher than the natural one. Also in this case, we decided to analyze the ortho level provided by the European Motion Service, and you can see the box where the porto is located. And we wanted also to see all the previous works to better understand the evolution of the area. And here we can see a cumulated displacement time series obtained by using different time series acquired by different satellites. And what we can see is that the trend is quite linear about the subsidence phenomena. This is another works provided by Thierry, obtained using the combination of the two techniques, and even in this case, the area of interest it seems to be quite stable. And here are our processing data. Obtained using the Cosmos SkyMed images spanning from 2018 to 2022. And if we go with a zoom in the archaeological site, the only two anomalies that we can detect are related to the building that hosts the visitor center, so it's a new building. And the other one are related to some shelter that cover the ruins. So in this case, the archaeological site, it seems to be quite stable by the meaning of the subsidence phenomena. Analyzing all the measurement points of the area, here we are at about 2 kilometers by the archaeological site. We detect these anomalies that was related in this case to maintenance work on the railway. So going to the final remarks, what we have reached is that the main result of this study have highlighted the importance of using the European Ground Motion Service for preliminary studies. You have to understand that we have to deal with a really huge amount of cultural heritage. So for us it's important to know preliminary where and how to go to process other data with an higher resolution, spatial and temporal resolution. All this work becomes the input for the final goals that is set up, integrated monitoring system and mitigation and conservation plan. Thank you for your attention.
Any question about the presentation on cultural heritage and the EGMS? Michele, what's the question?
Hi, thank you very much for your presentation. I was just wondering if you follow any...
Please give your name first.
Oh, sorry, I'm Guadalupe from the Spanish Geological Survey. And I was wondering if you follow any criteria to select those heritage places? The criteria to select the hotspots, the heritage places.
Okay, we are choosing in this phase, because we are running in the first year of the project, the sites that are located near or very near to the coastal line. So this is because we wanted to start taking into account these characteristics of the cultural heritage. So it was just for this. And to be honest, the Roman Terme of Baia belongs to a previous project. And we were, they asked to us because they were facing to instability phenomena. So they already known there are some problems of rockfall, and then we started with this. That's why.
In this study, you use the ground motion the European ground motion service as a first layer of information, a screening to focus. Are you going to use it systematically over all Italy?
Now, yes. Now we think yes, because as I mentioned, the first case study started before the first release of the European Ground Motion Service. So that's why I show you the ortho level is just to have an additional information. But at this stage, we think to use it also for preliminary analysis and then go to with a focus. For example, for the first case study, the use of an high resolution data coming from Cosmos SkyMed, for example, so with changing the band is just to go on with the analysis. But in the case of Ravenna, the Sentinel-1 was enough to understand the phenomenon.
Any other question for this presentation? So if not, I will introduce the next speaker. I will speak Catalan.
Thank you.
This is the Centre Technologique de Télécommunications de Catalunya, Mr. Palama. You're welcome.
Good afternoon. Good afternoon, everyone. This talk is focused on the detection of ground deformation phenomena from precedent scatter site interferometry data, and this will be done in a systematic way on the European Ground Motion Service data set. The first objective of this work is to show a European data set of active deformation areas, and this will be done thanks to the availability of such a pan-European ground motion data set. This activity is in the frame of two projects. First one is a Living Planet Fellowship, Wide Area Sentinel-1 Deformation Classification for Advanced Data Exploitation. The second is a DG Code Project RAS tool, a European Ground Motion Risk Assessment tool. We will see first a description of the algorithm for the extraction of active deformation areas that we indicate with the acronym ADA. Then the first results about the European maps of active deformation areas. A validation activity will be conducted and is shown the first result on a case study in Valle d'Aosta, Aosta Valley in Italy. And last remarks will deal with a possible way to build a European label data set of ground deformation areas that can be used for classification purposes. Our European Ground Motion Service, we all know, I think, what it is. I just want to specify that in this work we are using the basic product of the EGMS. This is because of its high resolution. So we know that the basic product has the original resolution of Sentinel-1, so full resolution, and also because in calibrated and ortho products are obtained with the calibration against GNSS data, and this introduced slow-moving, slow temporal deformation trends that are associated to, for example, tectonic activity in Greece and Iceland, and to glacial rebound in the Northern Europe. And as we are more interested in local deformation phenomena, we decided just to go for the basic product. Yeah, the algorithm is basically an extension of the IDA-Finder tool to process the GMS basic product frames on a parallel processing implementation. The first step, so this algorithm processes directly the PS time series and velocities of the GMS data. The first step is an outlier removal stage, then a velocity thresholding using a threshold of 5 millimeters per year, a pixel grouping where we are grouping together neighbor PS points with a radius of about 50 meters. And this is where the actual polygons is created. Then we have a quality index we talk about later, and this is reliability, kind of reliability measure where we assess the reliability of the extracted polygons. And then the last stage is overlap purging. This is because that may be the case where two active deformation areas, two polygons are detected in the same area, but they are associated to two different bursts or frames of Sentinel-1. In order to remove redundant information, we decided to go for the wider between the two or more overlapping polygons. The final result is a map of ADA polygons, which are also associated to other data, such as number of PS points included, velocity statistics, and quality index. These are the two maps obtained from ascending and descending line of sight. We can see there are high concentration of polygons in countries like Italy or Greece, Iceland, and Norway, with a cluster of deformation active areas distributed around Europe. The number of polygons is quite consistent between the two orbits. So we have 340,000 for descending and 350,000 for the ascending line of sight. We computed also the intersection between these two maps. The intersection between ascending and descending polygons, of course, depends on geometry factors, acquisition geometry, and topography. But in this case, it's also can be used as a first assessment of consistency between the two results. And we can see that the total number of intersecting polygons is almost half of the original polygons extracted for each orbit, so 150,000 polygons. These are some numbers associated, distributed for each country covered by the European Ground Motion Service. We can see that the total coverage is high for in countries like Italy and Iceland. It touches 5,000 square kilometers, and decreases for example, Norway, Spain, and Sweden, Greece, and then it's more or less always smaller than 1,000 square kilometers for the rest of the countries. We also computed the spatial density of the polygons, so dividing the total coverage of the active deformation areas by the areas of the countries. We can see a very high density in Iceland. Is closer to 5% of the Icelandic territory covered by active deformation areas. We know that Iceland is quite a special case where there are quite many different deformation phenomena related to permafrost, to volcanic activity and tectonic activity. So this result can be also justified by this presence of different deformation phenomena in Iceland. The other countries where the percentage is higher than 1% are Italy, where the incidence is almost close to 2%, and also Greece and Netherlands, where for the other countries we have less than 1%, or also for many of them less than 0.5% of spatial density. In order to assess the reliability of the extracted polygons, we use a quality index associated to each polygon that has been extracted, and is calculated using the PS time series. This quality index is a combination of a spatial noise index, that is basically the mean spatial cross correlation over all the PS pairs contained in one polygon, and the temporal noise index, it is the mean temporal autocorrelation calculated separately on the PS time series. These values are quantized to 4 possible values between 1 and 4, and then the global quality index is computed using a lookup table. Quality index 1 and 2 are only considered because they are more considered as reliable. And for the European ADA maps, we see that almost 75% of polygons have quality index equal to 1. Another consideration is also related to the percentage of the distribution of the temporal noise index values and spatial noise index values for each QI class, and this we can see that the weight of the temporal noise index is a bit higher here, and almost 99% of polygons within the QI within the class of the first class of quality index have a temporal noise index also equal to 1, and this is not the case for the spatial noise index, where this percentage is a bit lower, so it's going to 74%, more or 73%. This may be done also to filtering algorithm that is implemented in the production of the ground motion service. The first validation activity of these maps has been performed on the region of Valle d'Aosta in Italy. This is a mountainous region in the northwest part of Italy, and its territory is almost totally prone to natural hazard. We can see here that the information provided by the Italian National Landslide Inventory concerns 2 classes. So the first class is about landslide with various types. The second class is related to deep-seated gravitational slope deformation. This phenomena is related to slow movement of large portions of mountainous slope that is induced mostly by gravity. And this is very slow, but can evolve into faster phenomena like such landslides, so can be also considered as a hazard. We have the total number of polygons in Valle d'Aosta is about 1,300, combining ascending and descending data. Yeah, this is just an example of on a zoomed area. We can see how in ascending and descending line of sight we have different distribution, different sensitivity of the PS time series, PS velocity with respect to the movement of the slope. In this case, ascending it may be a more favorable geometry to detect the movement. We can see there is a big deep-seated gravitational slope deformation area, and also local landslide, smaller landslide in this case. Here is also evident how the ADA finder algorithm is working, and we can see that most of the moving points are delimited, are selected as part of active deformation areas. Yeah, here we just show the result of the combination between the Italian National Landslide Inventory and our result, our maps of active deformation area in ascending and descending orbits. Most of the ADA polygons are intersecting or matching a deep-seated gravitational slope deformation, about 52%. For the landslide class has an incidence of about 10%. And for about 13%, we have an intersection between landslide and deep-seated gravitational slope deformation. This is the case where in which an ADA polygon is covered by both a landslide and the deep-seated gravitational slope deformation, may be justified by the fact that the deep-seated gravitational slope deformation can evolve into a landslide in some cases, and then this causes the presence of both classes. For the 10% of the polygons, we have no match here. Of course, this can include false alarms, but also areas that have not yet been mapped in the inventory. Yeah, so this validation activity can be considered also, can be exploited to create a training data set for future implementation of supervised classifier on wide areas. As just to resume, we have seen the creation of European maps of active deformation areas in ascending and descending orbits. If two active deformation areas intersect, we merge them together to form a single polygon. If there is no intersection, we consider them separately. In this way, we are building also matching with the validation labeling data. We are building a global label data set of active deformation area. This is only has been done only for Valle d'Aosta at the moment, but will be extended to other areas with different ground motion phenomena, for example, subsidence due to underground mining activities, or groundwater extraction, settlement on, or also volcanic activity. This is part of the future ongoing work that is aimed to derive, to use AI tools for the classification, automatic classification of deformation phenomena over the, hopefully over the European, whole European territory. Yeah, this is, in conclusion, we have seen a European, the main result is the European map of active deformation areas. This is produced from European Ground Motion Service data. This map at the present moment can be also used for application such as geological study or early identification of hazard exposure for infrastructure and buildings. In the future, yeah, we have seen, as anticipated, we hope to derive an AI tools to classify the extracted ADAS. Yeah, this concludes my presentation, and thank you.
So we're going to ask if there are any questions about this presentation. There is one from John Dell, Norway.
Okay. Yes. Sort of connecting. Sigurd, you... Maybe I just speak loudly. Sigurd Janssen has a talk tomorrow entitled All Slopes in Iceland Are Moving, so I think he'll agree with your results. But seriously, will you make these data sets available, and how are you thinking of doing this training? Will you have some sort of crowdsourcing, asking people? Because of course it's not easy to just look at an ADA on a slope and determine the underlying cause. It could be rock glaciers, landslides, surficial processes, you name it.
Yeah, so we are in the process of publishing the data set, of course, and yeah, we are ultimating the publication of this, especially in the last step were a bit more complicated. It was a bit. We have downloaded the update of the ground motion service, and it took a bit longer than expected, but will be published soon.
Any other question about this presentation on the ADA?
Yes, I have one question. My name is Ana Paula from Lisbon University. I have two questions indeed. The first one is related with the threshold. It was not clear for me which criteria you used to select the threshold defined by 5 millimeters per year. And the second one is related with the definition of the polygon. You have done that in a GIS software. The definition of the boundaries of the polygons. How have you done that?
Yeah, well, the boundaries were just using a buffer function with 10 meters radius. And then about the velocity threshold, it was chosen mostly by experience. So we have been trying for some regions, and then using the threshold. That is a trade-off, because if we use a lower threshold, maybe there are a lot of data to process, and it's slow a lot.
I have one question. Is the ADA only looking for motion anomalies in areas that are sensitive to PSI, to the INSAR method, and what happens with shallow landslide that have a large deformation that are not compatible with the ability of Sentinel-1 INSAR.
Well, it's yeah, the tool is based on the analysis of PS time series.
So you look for the keys below the spotlight.
Yes. I think the most relevant novelty of the tool is to being able to select to extract information from such a big data set.
So and maybe it's a feedback for EEA that for the EGMS in the future, we should combine Sentinel-1 INSAR with other sources to be able also to monitor velocities in a range that is not addressable by INSAR.
Yeah, of course.
Like Planet time series or Sentinel-2 time series.
Yeah, so using different...
But there are many areas where you don't have any ADA, red or blue, but there is big deformation, but INSAR is not able to measure them.
Yeah, of course. Yeah.
Okay.
Yeah.
C'est la vie. So we go now to the roundtable.
We have the open questions, the seat question if you want to stay. You are invited.
And
UK EGMS meetings. Yes. We're going to miss the discussion on the EGMS. It's not just the UK. We have a meeting for an hour.
Ciao.
So for the participants who are interested into the roundtable discussion for this session, we have identified 6 questions, and we will gather any comment or any additional question. So the first question we have is the current EGMS implementation meeting the objective, which is full resolution, pan-European, updated every year? Is it delivering what it has promised? The second question is the loss of Sentinel-1B affecting the ability of ground motion service? The third question is, how well does the EGMS service combine with the other terrain motion services used by the community? For example, beyond the annual measurement, you have to customize measurements for the last few months, and you want to combine the EGMS product with other products that are accessible to the user. The fourth question is for the short term. What are the performance criteria? What performance aspect of the EGMS should be improved according to you? Different aspects on the data, the processing, the dissemination, and so on. The fifth question is, should the scope of the EGMS service change in the midterm? And the last question, that is a generic question for almost all the sessions of FRINGE, is have you identified any targeted R&D action to be made to make this more useful? For example, the link to the biomass, to the Roselle or Sentinel-1 next generation. So first of all, we go with the initial question. So the EGMS is an entry-level product, a public service, open and free. So anybody is happy to say that it does what it should do? Or somebody has to say it should do something differently to meet its objective? No comment means everybody's happy. We just record comments. There is one comment at the end of the room.
There are places where there have been earthquakes in Europe, and I think the validated product, I'm not so sure about this, because you can see that there's not a linear nice behavior, but there have been earthquakes, and in these regions, you can see that the time series look awkward. So for instance, there has been an earthquake sequence in Greece in 21, and when you look into this area, it looks like a pre-seismic signal, which is strong, yeah? Nature publication material. But I think it's some spilling in from some GNSS data that have been used there. I've talked to colleagues about this, but also from the service, but I never managed to write a good email about this issue. There are other earthquakes also in the region Balkan, something. So my recommendation would be to think about how these areas can be like cleaned of the signal if possible. If not, if there's some warning or something like this, because it could be read in a wrong way.
So the comment that we record from what you say is that some type of deformation pattern are not well captured by the GMS, for example, earthquakes.
Yeah, I think the earthquakes are affecting some ground assumptions of the time series processing in a not good way, so that the product is compromised. And this needs to be dealt with in some way.
Thank you.
I'm not the expert to give recommendations how to, but...
All right. Any other comments, positive or negative, concerning point 1? Oh, there's one comment.
Yes, following what just been said, it also happens in La Palma eruption. So the time series, instead of seeing the jump, I think so the filter, you can say as if the intrusion was linear in time, when we know it was a jump.
So what is the comment? That
it will be great to have some kind of note that in those regions, because of the filter, maybe the time series are not capturing well the movement.
So you lack metadata informing on the ability to detect some measurement?
Like that.
This is an option, a second option. I would like to, I don't know if you can comment on this, if is required a local processing or not?
It's a starting point, GMS, no?
As was, I think, correctly pointed out also in the documents, it's something to start having finally an EU-wide service. For sure, there is room for improvement, also because it was quite a challenge to have 4 independent processing chains and finally getting something harmonized or largely harmonized compared to the first results. So it's also related to question number 6. No, there is room for R&D activities. For sure, whenever there are abrupt changes in displacement time series, having also different phasor wrapping algorithms in the 4 different processing chains, you can have a different level of accuracy in the final results. But yes, for sure, it's a very relevant point.
But the hard fact is that some motion patterns are not measured, and nobody is saying that there should be any reprocessing and the EGMS becomes an atlas of deformation. It is what it is, and it has to be complemented by other processing outside EGMS. No, that's what I understand. I don't know.
I think it's a process and it's not clear in what direction it goes.
We don't know yet. Okay. We should have probably recommendation for in the future in-depth consultation of the stakeholders to see if this should be defined more precisely. Okay.
About this starting point, I have a comment. It is a starting point, but we hope to satisfy a lot of application already with this starting point. We don't have only to focus on the future improvements. We have something valuable. We got now through a validation process which was basically positive, already positive. So really now it is spreading the word and hoping to have as many applications as possible. Then it makes sense to go to the second iteration of improvement. This is my...
So maybe we go to point 2, which is, oh yeah, there is another comment on point 1?
Yeah, no, it's a combination of point 1 and point 6. Andre Kalia from BGR, Germany, and it is a great starting point of all, and it's highly acknowledged from my side. And what regarding rigorous are the actually the of highest priority, because these are the nonlinear areas where we would expect yeah, at least a high level of hazard. Thank you.
John?
Sorry, just one last comment or two. First, in terms of all of these suggestions will be very useful for EGMS, but in terms of timing, already the next request for tender for the next period, which will go from 2025, will already come early next year. So anybody has any comments or questions or recommendations, put them into EEA now, because otherwise you have to wait another 4 years. But also in terms of the quality and things like these type of capturing all types of ground motion, you have to consider the magnitude of the scale of the project. We're producing 10 billion measurement locations in a very automatic, it needs very automatic processing. Certainly if we wanted to implement full 3D phase unwrapping everywhere, that would be possible, but we would need to have 10 times the budget.
Thank you very much. Let's go to point 2. Is there any comment about the implication of the loss of Sentinel-1B concerning the ability to deliver a ground motion service for the EU space? Does anybody have any comments? So now we operate with a 12-day temporal sampling, and you can deliver the product this way.
We see no impact.
Okay.
Forget about Sentinel-1C.
So no major comment. Let's go to point 3. So point 3, the EGMS is providing an annual measurement, and many users or specialists receiving this product for end users would complement it with additional EO measurements. For example, to cover the time gap between the delivery of the EGMS and the moment of the project. So is the EGMS well integratable with the other measurements, like combining SBAS or PSI chain together with a basic EGMS product? So is there any comment about this compatibility? Ricardo?
Let's say partially trying to answer to your question. There are some issues that I would like to point out, although I already mentioned within the validation process where we are involved. Many users are noticing that if you look at the easily available full resolution products from EGMS, mostly the signal is dominated by the GNSS signal. So if you go in central Italy, if you go in northern Sweden, if you go in Greece, the signal is totally dominated by the GNSS signal. So I think, and because they do not have the information to understand what is GNSS related and what is DINSAR related, I think this is something that we have to provide, because the key point of EGMS is the differential SAR interferometry information. The GNSS is an external source, so I think it's essential, absolutely essential, to give to the users the differential SAR interferometry information, plus the GNSS information so that they can understand which is high spatial frequency, DINSR, and which is low spatial frequency, GNSS. Otherwise, as it happened to me, they will understand that DINSR gives to you the absolute information of the tectonics. That is something that we know, it's a relative information. So this is the first point.
But in the case of a user combining the GMS with his own processing to cover the last 4 months with his own chain, shouldn't he then consider the level 2 and not the level 3, no GNSS?
Let's say it's important to give the chance to understand what is coming from interferometry and what is not coming from interferometry. I think it's essential for them, because we have to accept that not everybody has the competence of the people in this room. And so for them, maybe it can be difficult to understand that there is an unwrapping, a reference point, and so on. And also with respect to the reference point, you know, this is a concept that for the user, it's not very easy to understand. How many reference points there are? 1 per burst, 1 per frame, 2 per burst. These are information that we need to understand. For us, everything it's easy, but for them, it's complicated to understand. So this is another issue that I think should be considered and is fitting this. And the third point, I didn't understand, but somebody mentioned the fact that the jump of the earthquake. I think as an INSAR scientist, my point of view is that on the atmospheric filtering, there is still a lot to do. So basically, we go there and mostly we make space-time filtering. And so sometimes something goes in the filter or not. I think we have to seriously think about the fact of giving to the users also non-filtered products together with the filtered ones, because this is another issue which is very important. There is even signal, let's say, in the atmospheric component that we are removing. So I think that the community is mature to look also at this tremendously noisy time series to understand that there is this atmospheric information that perhaps it's tricky and interesting information for them to be understood. So to summary this long story, GNSS and INSAR separated information, referencing clearly, and atmosphere, not atmosphere, because you saw yesterday there was an entire session, so we have to be very clean with the users and give this information to them. The last very brief point, phase unwrapping, that's a very complicated story. You know, I think I have probably 35 papers on phase unwrap. It's an ill-posed problem. I've built up my career on phase unwrapping. It's a really very complicated problem. Very likely with Roselle, with NISR, with this L-band, we can get a nice support to phase unwrapping, but this is a really tricky problem. So on this, I think, Andre, I agree with you, it's a problem, but we do not have to create big expectation, because I think this is really very, very difficult to be fixed.
Okay. So maybe we move, oh, there's another comment from Lantmäteriet, Sweden.
Thank you very much. Actually, I mean, EGMS is great, but one wish, John said that maybe now is time for wishes. Now, GI, Geological Institute, and Traffic Verket, which is for the railway, roads, material. So the GI signal, so we have a dominant signal in Nordic countries at least. So people wish for visualization of basic products. And I have mentioned this to Lorenzo and Joanna, that we wish to have visualization for the basic products. I mean, now we see the ortho, calibrated, but not the basic ones. But at least if it can happen for, I know, I mean, Europe is large, but at least for areas that we have this GIS signal, if we can visualize the products.
Thank you very much. We go to the next point, which is for the short term, what should be done from not from an expert viewpoint, but then from a user viewpoint to achieve awareness, acceptance, and adoption? What should be done that is not done today? So EGMS is being produced. User organizations use EGMS and use other chains. EGMS has a validation activity. Europe is full of public and private providers that deliver services. What do you think is missing for a better adoption of the technique in the community?
Maybe that is in the Jupyter notebook. So if somebody wants to reproduce the data for a small area, is it possible or it's not possible?
The Jupyter notebooks were concerning the validation, not the production of the data.
Okay, I think then that is something what would be very useful, to have the ability for a small area at least to repeat the results, even if it's not quite the same as the product. It will give the user confidence, having exactly known how it was done.
So, sorry, what is the proposal? So I didn't get...
Some Jupyter notebooks where you can, for a small area, do your PSI processing in a, maybe not quite in the same way.
But this requires to publish the processing tools, or...
Yeah, we are in the area of open science, so I think to use data in a publication if you don't really know how it was done.
John has a comment.
Thanks, Falk. We are scientists producing the data, but it's done on a commercial contract using commercial software. But in defense, if you go into the website for the European Ground Motion Service, you will find very well documented the algorithms that are used, the basic science behind it. There's an algorithmic theoretical baseline document, which is some 100 pages long, which outlines everything. If you want to do it in a similar manner, as you say, you can go onto GTAP and use the same Sentinel data and use various basic PSI tools to do something that's similar. But if you want to do the
JEP.
The JEP, yeah. So there are tools out there to reproduce the data. But if you want to exactly reproduce the data, that's not going to. Because the providers are being paid to provide data, not to hand over their commercial software.
Just one comment here. The geohazard exploitation platform, the JEP, is able to ingest and publish all the EGMS products, and that allows the community to go there and look at them and compare with other processing chain and do some further processing.
A comment on your comment is my feeling is that the need to reproduce the processing would probably interest a very small fraction of the users. What we are targeting with the Ground Motion Service of Europe is to have a very wide range of users coming, especially not from FRINGE or from all the community around, rather geologists, geotechnicians, etc., etc. And my feeling is that it's much more important to put the focus on the data, how to understand well the data, okay, rather than giving the possibility to reprocess.
Yeah, but just looking ahead, I think, for example, the journal from the American Geophysical Union, to get something published there what was processed with RadarSat, I think it is impossible even, because people can't get through the data. So things are going to be stricter in the future.
Any other comment about what should be done to increase acceptance and adoption by user communities for the ground motion service? There is one comment from Chaos.
Yes. Can you hear me?
Yes.
Yes. My name is Roland Akiki from Kairos. So it's not, it's maybe already there, but my question is there a programmatic API to query the catalog for the data to get a link to download it from, let's say, a Python program? And that's one thing. You can download the whole product, but can maybe also a subset of the CSV.
So that's a technical question that ESA and EA discussed in the last months. Maybe Jose Manuel can answer this question. I think the answer is no. So all the EGMS products are also ingested and published on the Geohazard platform JEP, and there you can apply APIs. In the midterm, Lorenzo Solari told me that EGMS portal will include APIs in a way to do what you say, but today it's not the case. Is that correct, Jose Manuel?
Yeah, I think so.
Any other comment on that point? So we go to the next point, which is midterm. Should the scope evolve? That's a very broad question. I made a comment before that we only look for the keys below the spotlight. So INSAR only measures millimetric or centimetric motion. Other techniques measure metric deformation or larger movements, but we only talk about this range of deformation. So that's one way where maybe the scope could evolve, but it's super ambitious. Another aspect of evolution is going to L-band INSAR, and we had a very nice presentation this morning about Roselle, for example. So what do you believe about the scope? We have a scope today, and we know what it is. It's C-band, it's annual deliveries, it's full resolution. Do you think something should change in the scope for Europe? It's a very open question, because somebody will say everything should change. We talk about an entry-level open and free service. So maybe the first thing to say is that the message of EEA is that EGMS will continue, and the first area of evolution is the integration of L-band in the future. I don't know if it is a commitment, but it's an intention at least.
Even before that,
Micro?
We are always quite biased, no, to think in terms of phase information. And of course, we are here at FRINGE, and everybody talks about phase and fringes. But probably before going, adding to C-band, L-band, X-band, P-band, we could consider at least the amplitude data, because it's a huge amount of information there, and as a matter of fact, we process the data stacks, and typically we forget about the amplitude data. Probably it's something worth considering once we start discussing about the scope of the next, say, contract, whoever will be in charge. Just food for thought. Change detection, basically, because INSAR is a sort of coherent change detection. But now we are so focused on phase data that typically we don't consider the information of amplitude.
You mean not for improving the processing, is for really change detection?
Yeah, because probably we are using amplitude data to improve the phase, so the final results in terms of displacement data. But as a matter of fact, people are also interested in looking into the images, no? And it's a shame that we have sometimes thousands of amplitude data there ready, but simply are not available for the general public, for journalists, for no. Sometimes it's important also to show amplitude data. Sometimes speak for themselves. No? Now, for example, no flooding and so on.
Any other comment about this topic of evolution of the scope of the EGMS? Michael, einde daar? Microphone there.
Yeah, you mentioned it, observation strategy, no? Even if you stay with C element, of course, but the north-south component is not really solved, and changing satellite orbits, using spectral tracking, whatever, but the problem is there, no? So this could be one thing to work on or to think how to improve that.
Nuno, you have any comment about this suggestion to look at the north-south component with?
Okay.
Okay. North-south component. Yeah. Okay, so let's move maybe to the last point. If we are able to identify any targeted R&D to be done, it's an interesting message to ESA because we have an EO program. And with the EO program, we can maybe take some of these and open new activities to address them. So if the audience has anything to say about some R&D that we should do with the idea to improve the context of a pan-European ground motion service with innovative stuff to complement what is done by the Copernicus EGMS with additional activities that are more innovative. You don't have to speak now. There is one comment.
Yeah, maybe from the north-south component. Yesterday or today, somebody said something about the burst overlap in processing and looking for the north-south component. Maybe this would be something that could be done to get closer to something like the north-south component. Or any research to get the north-south component out of the existing data.
Just to illustrate how important it is, the big landslide that is blocking the railway between France and Italy, between Lyon and Turin, is a landslide facing north and is very difficult to capture with INSA.
Yes. Not only tectonics and volcanics that we learned today in Harmony, but it's also north-south orientated landslides that are important. And also on infrastructure, you have north-south movements that you can't see with the actual ground motion service.
And what about R&D to be done to prepare for the combination of Sentinel-1 INSA with biomass, Harmony, Sentinel-1 next generation? Any ideas welcome? In ESA, the process is open to capture ideas, obviously. There is one comment here.
Hello, Filippo Vecchiotti from Geosphere, Austria. I don't know, there will be maybe room for to add to as a visualization, an extra layer to visualize soil moisture data. That will be for many people, good because maybe the quality will change because it depends. Maybe it will be 1 kilometer product, could be Sentinel-1 derived product, could be 25 kilometer product, but still could be useful for the interpretation, I guess.
But it is not an R&D topic. It is available, isn't it?
Yeah, but it will be nice to have it on top of the visualization of EGMS.
Okay.
In order to maybe also to analyze the time series, because they could be even daily data, so even on a temporal scale.
Just to be clear, as it is today, the EGMS is a production capability delivering products with a dissemination portal. It is not a processing environment with the ability to do complementary processing online. So,
I know.
No, just to make it clear.
Yeah.
Okay, point taken. So what you suggest can be done in different contexts, not necessarily on the production facility. Michael?
Yeah, once again. We heard today phase unwrapping problems affect the current product. And I mean, with L-band, the key would be there to do dual frequency phase unwrapping. So having an approach that takes all the data together for an improved product could be interesting as soon as L-band data becomes routinely available. It could even start with NISAR before Roselle.
I can tell you that Michele Crosetto is not a doctor because I can read what he writes. He writes a lot. Any comment from you about point six?
No, I have a final comment when we finish.
Is it time to finish, maybe?
Probably.
Okay. One comment.
Maybe when we think about future and I mean next missions and Sentinel-1 and others, so now we know that many corner reflectors around and there are, I mean, more being set up in different countries, for example, in Sweden and Finland. And I'm just thinking what is the best way, but probably starting with a database, if already is not existing, database of well-constrained corner reflectors or transponders that we know the exact, I mean, location, and then maybe they contribute for future calibration, validation, or generating them. It may help maybe to start at some point, I mean, some kind of database. I don't know, as a suggestion or already maybe it exists.
Okay, thank you. There's one more comment.
As we talk about R&D, I have some sort of non-persistent scatterers, for example, in coastal areas with tidal waters. There you have non-persistent scatterers, for example, groins and so on, that are sometimes below water and sometimes above water. And they are not found by the EGMS right now. So this kind, or especially also in rivers, where you have the riprap or so, this is in high water, below water, and can be seen, and in low water it can be seen. So these kind of non-persistent scatterers should somehow be addressed, and this is probably something for R&D that can be done in the next years.
Good. So we are about to close. Before doing this, I would like just to reinforce the message of John of before. In the forthcoming month, is going to be defined the tender, the new tender for the production. So these days, these weeks, forthcoming weeks are key to collect ideas. If you have ideas for the evolution of the service, please write to Lorenzo Solari from the European Environment Agency or to myself, which represent the advisory board of this service. Okay? And we will collect this information. This said, thank you very much for coming and for the contribution.